Okay, so I think we can start, right? So, hello everyone. Good morning. Welcome back to the school. So it is my pleasure to introduce Xavier Carreras, who has been with us in the summer school since the very first edition. So Javier is currently a research scientist at the Artificial Intelligence Research Institute from the Spanish National Research Council. The institute is located close to Barcelona. So over the years, Javier has served the NLP community in numerous roles. He was, for instance, the program co-chair for EMNLP 2016. He was president of the ACL Special Interest Group on Natural Language Learning, which organized the conference from 2014 to 16. And his research has also been extensively recognized. I'm sure that many of you are probably familiar with his work on machine learning methods for NLP in applications like information extraction and named entity recognition, syntactic and semantic parsing, machine translation, and many others. So his lecture here today covers learning with structured predictions or predictors. We'll be using pre-recorded materials, but Javier, maybe you want to say a few words in the beginning?
Well, of course, I want to say hi to everyone. I'm very happy to be here one more time. I thank all the organizers for setting up this school. I think it's a great school. And well, I hope you enjoy the lecture. I'll be here for questions, so don't hesitate to ask questions through the chat.
Okay. Thank you.
Hello, everyone.
I guess we can...
My name is Xavier Carreras. I work for Metrics, a startup based in New York, even though I work from Barcelona. This lecture is about learning structured predictions. I'm gonna discuss a structured prediction in the context of supervised machine learning, in the sense that our goal is to learn to predict, and we're gonna do so by having a collection of training data, namely examples, where an example is a pair of an input together with the correct output. And we want to learn a function that is able to predict, namely given an input, we want the output that better corresponds to the input. And of course, because this is learning, we care about generalization. So we want a function that will work well for inputs X that we have never seen in the training data. So this is supervised prediction, and it is very common to get introduced to these topics with binary classification or even multi-class classification. So in these two settings, the outputs are just atomic scalar values. So in binary prediction, the output values are negative or positive, while in multi-class, we extend the approaches to consider one of many possible labels. So the contrast of structured prediction approaches is that we want to learn functions that the output is a structure. So for sequence prediction, the outputs are sequences. In context of natural language processing and parsing problems, the outputs are syntactic trees, and so on. Now, typically, whenever the outputs are structures, the inputs are structures too. But there's also tasks where the input is a structure and the output is just a binary sign. This would not be structured prediction. What makes the essence of structured prediction is that output values are structures. I'm going to give now a number of examples. One of them is name entity recognition. And the simple definition of this task is as follows. The input is a sentence, namely a sequence, and the output is also a sequence of labels with one label per input word. Now, in this case, this label indicates that Jim is part of a person name, while 300 is a quantity, and Arme and Corp are part of organization names. This is also a label that indicates that shares or of are not part of an entity. So what makes this problem difficult? Well, like in most natural language processing tasks, ambiguity is something that is very challenging. So for example, in this example, London typically is the name of a city, so it would be a location. But in the context of this sentence, Jack London went to Paris, it is the last name of Jack London, so it's a person name. While here, Paris changes the label because Paris Jackson is a person name. while London here is a location. So the same words, depending on where they appear, they can function differently. And so the labels in name entity recognition try to make this disambiguation. That's not the only challenge. In many cases, we will find words like Lisbon that we've never seen before, but for some reason, they look like a location, perhaps because this looks like a known location, namely Lisbon. So there's features of the word and the characters of this word that make it similar to a location name, but also for the context where it appears. So these are important challenges. And while I'm telling you that this is about predicting sequences, you might be thinking, well, what I need to do here is to predict one label for each word. So I can view this problem as a series of multi-class problems. Namely, for each word here, I'm going to predict what's the corresponding label. And this approach can go very far. There's a lot of good reasons to treat these tasks as multi-class, as a series of multi-class problems. However, what makes a structured prediction essential is that somehow we have prior knowledge, or maybe it's just a belief, that it's not only, we not only want to model the relation between inputs and output labels, but we also want to model statistical dependencies that exist between output labels. So namely, when we're predicting that this is part of a person, we somehow knew that the surrounding labels are these ones, person and nothing. It would probably be easier to predict that this is a person name because it's following a person name. So while the information that this is a person name is somehow in the input sentence, we would like to consider approaches that somehow can take into account that these two labels are next to each other and these two labels next to each other. So somehow in structured prediction, we'd like to exploit the fact that there's a statistical dependencies between inputs and outputs, but also between parts of the outputs. And we'd like to understand the type of functions that allow us to have these representations. So here's another task that also falls under the general task of sequence labeling. It's part of speech tagging. So like before, for every word in the input sequence, we want to predict a label. But in this case, the label is encoding the type of syntactic function, the syntactic function of each word. So again, the problem here is ambiguity. So flies can be a noun or a verb. It's typically a verb. The bird flies. But in the context of this sentence, actually, after reading it, one can figure out that this is actually the fly, the insect. Okay, so it's a noun. So again, here, and to make this prediction, if we could know that the surrounding words are noun and verb, it would probably be much easier to figure out that this is a noun. So the question is, if we don't have any of the labels, how can we have a function that makes these predictions as if these word labels were available? So a structured prediction is not only about predicting sequences, it's also about predicting trees. So a very common task in NLP is syntactic parsing. Here it's in the form of syntactic dependency parsing. The input is a sequence, a sentence, and the output now is a tree. That a tree built of syntactic dependencies, like this one. So while before it was perhaps pretty straightforward to think of sequence labeling as a series of multi-class problems because we're predicting one label per word, here it's really less straightforward to reduce this problem to a series of classification problems. It's not clear what we would predict. In addition, because we're predicting trees, we need, when we build or predict the output structures, we need to somehow make sure that the output is a tree, in the sense that it is a well-formed structure, that there's no loops, etc., etc. So the approach, the set of techniques we're following today, we're describing today, also extend to more challenging prediction problems like predicting trees. Another very important problem is machine translation, which in its form can be also seen as a sequence prediction problem. The input is a sequence, maybe a sentence in some language, and the output is another sequence, which is a sentence in another language. So here we're translating French to English. So while these are two sequences, there's not a direct correspondence between words of the input sequence and words of the output sequence. So again, so this makes this is one of the challenges of machine translation among many challenges for that problem. But I want to highlight here that, first of all, it's not obvious how to reduce this to a series of classification problems because the correspondence between input and output words is not direct. So we need some sort of alignment to do this. And second, the same essence applies. So it is clear here that whenever, the way we do it, whenever we're predicting the output words, we'd like to predict them ideally all together, conditioning on each other, okay? And just the last task I want to illustrate for this family of structure prediction problems is outside natural language processing. So in computer vision, we have object detection. The input is an image. The output is a grid where each cell of the grid has a label indicating what kind of object is in the grid, in that cell. So for example, we might have here that this is labeled as wall, this is also labeled as wall, this is labeled as the ground, and maybe this is part of a tree. So again, if when we are trying to label this cell here, we somehow knew the surrounding labels, it looks like the classification would be much easier. So how can we predict all the cells all together, taking into account adjacent information? So this is the goal for today, introduce the basic concepts behind a structure prediction. And to make things simple, I'm just going to essentially focus on sequence prediction. And as a matter of fact, I'm going to focus on sequence labeling, which is a very simple form of structure prediction. But yeah, that will be useful in order to illustrate what are the challenges. And one of the aspects I want to insist is that, as of the previous lectures, we already saw a number of techniques for classification, and those include learning paradigms, theory, ideas about how to generalize, ideas about representation, algorithms, etc., etc. So what is that we can borrow for the structure case? And the idea is that everything essentially works for this setting too. But there is an additional problem in structure prediction that the computations are prohibitive. So we need to adapt the previous techniques for binary and multi-class classification in such a way that the resulting algorithms will be computationally efficient. Okay. So the main topics I'm going to cover are, I'm going to start with the families of models behind structure prediction, putting the focus on transition systems and factored models. I'm going to insist a lot on feature representations of structured input-output pairs. We're going to also look at prediction algorithms, namely how to do the predictions. And only after all that is covered, we're going to look at learning algorithms in the sense of the algorithms that, given annotated data, they estimate the parameters of a model. And that will allow me to discuss the notion of global and local versus global losses for learning. Okay, so this will be essentially what I'm covering in this lecture, which is certainly not everything that is relevant for structure prediction. So things that I'm not going to discuss are detailed overviews of NLP tasks. I'm going to use name entity extraction just as a task to illustrate, but essentially with toy sentences. But if you really want to get expertise on name entity extraction or any other task, this is not the lecture for that. You should check tutorials at ACL, overview papers, or just papers that present models for that. So I'm not going to describe that, nor evaluations or state-of-the-art systems. This lecture is structure prediction using linear models. So when it comes to predicting structures, one technique that is very important is the ability to induce hidden representations between the input and output structures. Okay, that these input representations, the input structure, these hidden structures should facilitate the prediction. Okay, so this I'm not focusing, even though it's a very important topic in structure prediction. But as a matter of fact, the upcoming lectures, which are on neural approaches to structure prediction, so neural networks are in fact inducing hidden structure between input and output structures. So I'm not going to cover that, even though I'm going to mention why this is relevant. And finally here, I'm not going to discuss unsupervised learning. So here, I'm assuming that the representation, the specification of output structures is already given. And as a matter of fact, I'm also assuming that it's supervised learning in the sense that I'm given a collection of examples with input and output structures. So I don't need to care about how should I design output structures that explain the data in the way that I want. Okay. So while this can be done, so this task of specifying the output structures can be done either manually. So linguists do that when they annotate large corpora of syntactic or name entity information. But you could also try to have an unsupervised learning approach that, given sequences, induce a structure in the form of sequences or trees that explain the data. Okay, this is a very appealing and important challenge in NLP and AI in general, but I'm not going to cover approaches for that. This is the plan of the lecture today. It's divided into 3 parts. Each part is roughly 1 hour, and there's one video for each part. So in part 1, this part, I already covered the introduction. Next, I'm going to show 4 high-level approaches to sequence prediction, and then we're going to quickly see greedy methods to sequence prediction. That will conclude the first part of roughly 1 hour. Then in the second part, I'm going to focus on a family of models that I call factored sequence prediction, and we're going to look at algorithms to make predictions with this family of models, and also a probabilistic version of these models, namely log linear factor models. Okay. Only after I cover all this material, then in the third part, we're going to actually look at learning algorithms, namely algorithms that, given a certain model for structure prediction, estimate the parameters of the model using label data. Okay, so we're going to look at 2 kinds of learning algorithms, namely structure perceptron for structure prediction, and also log linear models and conditional random fields. Okay, and at the very end, I will give a very quick overview to dependency parsing, just to see that all that I'm explaining here also applies to other kinds of structure prediction problems, and I will conclude. In this section, I'm going to describe approaches to sequence prediction. For the sake of simplicity, I'm going to focus on simple definitions of sequence prediction tasks. In particular, I'm going to talk about sequence labeling, as in the following example, where the input is a sequence and the output is a sequence of the same length that has 1 label for each element of the input sequence. Let's look at a more formal definition of this task, which will allow me to introduce some notation. I'm going to use X in bold to denote input sequences that are of some length, okay, and where each element belongs to some space of input elements. So in the case that we're dealing with sentences, this will correspond to the domain of words of the language. The symbol Y will denote a sequence of labels, and typically for an input of length n, we will have a sequence of length n with 1 label for each input element. Now, the labels, each of the labels is of a set of predefined labels, and we assume there's a relatively small number of labels, which could be 10, 50, or even 100. Okay, but this is predefined. So in the context of supervised machine learning, the problem is as follows. We're given training data, which is a collection of examples, and each example is a pair of an input sequence together with the output sequence. And the goal is to learn a function, a prediction function that can map input sequences to output sequences, such that it works well on unseen inputs. So rather than describing learning algorithms, we first need to understand what is the form of these functions that we are going to learn. And that's essentially the main content of this section, describing different ways where we can model this type of prediction functions. So I want to make sure that there's a detail which has to do with the length of the sequences. So this function should work for sequences of any length. The situation in sequence labeling is that given an input sequence that is of some length n, the output sequence has the same length. But in a certain collection, the different examples will have different lengths. Okay, so in all of the discussion in this section, I will be assuming that this is the case. Okay, so I will now describe families of models to implement this kind of functions. So let's first, however, understand an important property of sequence labeling or sequence prediction in general, namely that the space of all possible outputs is of exponential cardinality. To see that, let's consider a set of output labels that is just this, with just 3 labels, and let's consider an input sequence. So underneath each input element, we're going to write all possible labels for this element, and so on and so on. So this gives us a graph such that a path in this graph corresponds to one solution, namely this blue path here is giving label person to Jack, person to London, nothing to went, nothing to two, and location to Paris. So this is one possible labeling, while the red path is another labeling. So any path in general is one possible labeling. So if we want to count the number of possible outputs for a given input, we can see that this is exponential, because if the input has size n, then the number of possible paths is the number of labels exponentiated to the n. So because we are dealing with functions that need to select one solution out of an exponential number, we need approaches that can deal with this in an efficient way. Okay, it's just not possible to enumerate each possible path by brute force. Okay, that would be unfeasible. So next, I'm going to show 4 different high-level approaches to cope with this exponential number of solutions. The first approach is perhaps the simplest one, and I'm calling it label classifiers. It has to do with, instead of treating this problem as predicting a sequence, I'm going to treat it as predicting one label for each input element. So there's going to be a series of multi-class predictions, one per input element. So in terms of modeling, I will describe a little bit this model and the notation I'm going to be using. So we will define a model that will produce scores for assignments of labels at a certain position. So namely, X denotes here the full input sequence, T is a certain position, like this one, and L is a possible assignment of label L to this position. It's a possible assignment of person to this position. So now, in this approach, we will define a model that, given this candidate assignment of this label to this position, it produces a score. Now, what is going to be the label that we assign to position T? I'm calling this Y hat at position T. So to make this prediction, we're going to consider each possible label in our label set and have our model predict the score. And we're going to take the argmax, namely the label, the argument, that maximizes the score. Okay, so this is really analogous to multi-class prediction. Okay, a multi-class classifier chooses the label that maximizes a certain score. Here, we're going to do the same for each position of the input sequence. So the question is, what is our model? What is the score function? If we look at learning functions that are linear, this score will be given by a product of a weight vector and a feature representation of this assignment. Okay, so in particular, this function returns a feature vector of D features that represents the assignment of output label L to the position T of this sentence, while W is a weight vector that will be learned and that has one weight for each feature that we specify. So what is good about this approach, about this kind of representations? Well, in sequence prediction, in tasks like name entity extraction or post tagging, there will be a number of clues of the input sequence that are important in order to decide the label. For example, the current word is London, the surrounding words, the fact that these are capitalized. So many features of the input and the context of this assignment give us lots of clues about what is the possible label that should be assigned in this position. So this function can capture these interactions between the full input and one single output label. However, in the context of a structured prediction, we wanted to capture interactions between output labels, more than one at once. So because we decided to treat each position independently of each other using multi-class, this is not possible. So I'm going to extend this approach to have interactions between output labels. So this brings me to a second approach, which belongs to the family of transition-based sequence prediction. I will discuss this family of models later. It's also called greedy prediction. And it has to do with the fact that even if we do a multi-class prediction at every position, we might fix the order in which we're going to do this. So we might just do these classifications in a left to right fashion in such a way that whenever we give a score for a possible label at this position, we already have the predictions of the previous positions. So in this kind of model, we can extend the scoring function of the model to include not only the input sequence, a certain position, and a label we are trying to assign, but also the previous labels we just assigned before the position. Okay, so this is exactly as the previous model that looks at one label at a time, but we are adding to the score function the prefix of predictions that are already done. Okay. The expression to decide what is the label at each position is still the same. It's a maximization over the labels we can assign to this position. The only difference is that we're adding the previous predictions. Okay. So this is good because now everything that we could capture before, we can still capture. But in addition to that, we can capture interactions between the full input sequence and the prefix of the output sequence. So while we clearly extended the expressivity of the model in ways that are very useful, one problematic aspect of this kind of approach is that our predictions are greedy. Namely, once we have assigned a person tag here, we must move on. And what if this was wrong? Was there a way to be more robust and consider other assignments that maybe make the following predictions better? As a matter of fact, with the way that we defined how we're going to predict the sequence, there's no notion of globality. There's no notion of what is the best sequence we could assign to this input sequence. And other questions we might be asking is, since we need to fix the order in which we're going to do predictions, why are we doing left to right and not right to left? So this is a directional approach of prediction. And so somehow, if we follow this approach, we need to have some idea of what is the best way to construct the full structure by little steps, by little actions. An alternative approach to sequence prediction is to use factored sequence models. So in this case, starting from the first approach where we predict the scores for individual labels, we're going to extend that, but in a different way. Namely, instead of predicting the score for one label, we're going to predict the score for two labels at a time. Okay, so this representation of two labels, I'm going to call them a factor. It's just a label diagram. Okay, in particular, so I'm going to extend the scoring function such that at a certain position I, my model can score a label yi that is assigned to this position and also the previous label. So for a certain position, my model will score the label assigned to this position and the previous one, and so on for every position. So I'm changing here the way I'm writing the expression to decide what is the prediction we're doing. So and here I'm introducing a notion of globality. So on the one hand, on this part of the equation, it's what my model is defining. So my model will produce scores for pairs of adjacent labels, for bigrams. But if we take one possible output sequence, a complete one, let's call this y. Y is a full sequence of n labels. I'm going to consider the sum for each position of these scores of pairs of labels. Okay, so note that a given label, so the label person assigned at this position will participate in two terms of this sum. Okay, namely the term for position I, but also the term for position I plus 1. Okay, when I'm considering the score at position I plus 1, the label here is also part of the score, right? So for models that scores pairs of labels, each label will participate in two terms of the scoring function. So coming back to our prediction model, for any full sequence of labels, I'm having this aggregation of scores. I'm summing the scores. So this gives me a notion of a score of a full input sequence together with a candidate output sequence, but a complete one. And so I will define a model that, given a certain input, considers, at least conceptually, considers all the possible output sequence and returns the output sequence that maximizes the score given by the model. Okay? So it turns out, so we, as I explained before, this space of solutions is exponential. But if we define the score of an input-output sequence as a factorized sum, then it turns out that we can solve this search problem in a very efficient way. So what is the advantage of factored approaches? Well, in terms of representation, we're now potentially capturing interactions between the full input X and factors of the output space. Okay? Instead of having a single label, now we don't have the full prefix of labels as in the greedy approach, but we have as many labels as we can add to this factor, right? The notion of factor is a general one. Here I'm using factors of size 2, but this in general can be extended to factors of higher order, factors that contain several labels at a time. So it turns out that for many types of factorizations that are very expressive, so the prediction is exact. And by exact, I mean that there exists an efficient algorithm that can recover the output sequence that maximizes the scoring function. Okay, so here, as opposed to greedy models, we do have a notion of optimality at the global level. So the fourth approach I want to discuss are re-ranking approaches. So in re-ranking approaches, our model is the most expressive one. Namely, our model scores directly a full complete input sequence together with a full complete output sequence. And so we express the prediction function as pick the output sequence that maximizes the score given by the model. So there's a trick here, because as we mentioned before, we cannot search explicitly through the output space. So, but the solution, the trick here is to rely on an active set. What do I mean by that? So we're not considering the exponential number of solutions. We're considering a small set of, let's say, 1,000 solutions, okay? And so this re-ranking model, restricted to the set of 1,000 solutions, will go to each of them, score each possible candidate, and pick the maximizing one. How can we obtain a reduced set in order to make this tractable? Well, so the previous approaches, the previous family of approaches, label classifiers, greedy predictions, or factor models can in fact be used, given an input sequence, to identify a set of outputs that is likely to be to contain the correct solution. So in re-ranking approaches, we have this notion of base model, namely it's a model that can select an active set of solutions, and that is done efficiently. And then after selecting the active set of full solutions, a re-ranker goes and does the scoring. So the main advantages here is that in terms of expressivity, in terms of features, there's no constraint at all, because the two sequences, the input and the output, are fully available. So overall, in summary, what I'm showing here, one of the take-home messages of this lecture is that in structure prediction, there exists an expressivity tractability trade-off that has to do with the fact that the output space in structure prediction grows exponentially with the size of the input sequence. And so, because there's no chance by which we can enumerate this output space exhaustively, we need to identify some sort of trade-off between the expressivity of the model and the prediction. Okay, so on the one hand, we can just look at individual labels of the output sequence alone, and then in that case, the prediction is very simple. Or on the other extreme, we can look at the full structure. Our feature representation can codify the full structure, but in that case, we need to limit the prediction to just search on an active set of predictions. So possibly the most interesting solutions are in the middle. Okay, and there's two main approaches. One is the transition-based approach, which is I'm gonna construct my output sequence, my output structure, in an incremental fashion in such a way that my model can make use of the parts of the structure that are already built. Okay, my model has access to the full history of decisions. But in that case, the prediction is greedy. It depends on the steps we already decided. The other approach is to think not of a construction process, but to think of parts of the structure that we want to score together. These are the factors. Okay, and in most cases, for many types of factorizations of output structures, there exist algorithms that can recover the exact prediction. Okay, so I don't think there's one solution in this map of solutions that is just the best one for any possible problem. It's a trade-off. So, you know, one paradigm is, given this trade-off, always pick the simplest approach that suits the task at hand. So the goal of this lecture is to present the type of models and to present the type of expressivity in terms of how are we representing the input-output structures in terms of the model. Okay, and then it will depend on the particular task you want to solve, which model is most appropriate. Okay, and it may depend on where
do we observe or do we believe that there exists these dependencies between parts of the output structure? Okay, and typically, state-of-the-art models will do a combination of these things. Okay, these things are not exclusive by themselves. So in the rest of this section, I'm going to discuss with a bit more detail these two family of models. Namely, first I will start with greedy prediction models, and then give the generalization for transition-based models. And after that, I'm going to focus on factor models, and I'm going to describe these algorithms that allow us to recover the exact solution.
So let's now look in a bit more detail to sequence prediction methods. Okay, these methods construct the output sequence one label at a time. And when deciding for a certain label, they use the previous predictions made so far. Okay, so then essentially the model defines a scoring function that takes an input sequence, a certain position, the label we are considering assigning to this position, but also these previous predictions that have been done in previous steps. Okay, so I will focus on two aspects for these models. One is what is the scoring function and how are the parameters using linear methods? What are the parameters tied to? And then later, I will discuss a generalization of greedy sequence prediction to transition-based systems, and I will describe a search for the best solution. So, okay, in linear sequence predictions at time t, our model computes a certain score. Okay, and in linear models, this is by means of a product between a weight vector and a feature vector that is representing this type of decision. So both they lie in the same space, say d dimensions. Okay, and here's a diagram showing a feature vector representing the assignment of a certain label in this position t of the sentence, given that we already assigned this subsequence to the previous label. Okay, so this is represented in a feature vector with features with t coordinates, and the model then has a weight vector that will be learned by the learning algorithm. Okay, so let's not forget what is the goal of this scoring function. The goal underlying the scoring function is to guess the correct label. Okay, so it should give high scores for the label that is correct, and low values or even negative values for labels that are incorrect. Okay, so I want to focus a little bit on how in practice do we construct these representations. Okay, and there's two main trends now. The new trend that has been established over the last 5 to 10 years is representational learning. Okay, neural models, they do learn a scoring function that is parameterized by parameters, but they also do learn a representation of the underlying decision. Okay, you can call that embeddings, whether they are contextual or not. Okay, years before deep learning achieved this success of representational learning, we defined these feature vectors, let's say manually, using feature templates. I'm gonna introduce this just to highlight what kind of features are in this feature vector. And so essentially what I want to discuss is what kind of weights the learning algorithm has access to. Okay, in order, let's not forget, to make these predictions correct. So let me, to present what are feature templates, let me introduce the notion of indicator features. These type of features are very useful when we need to represent discrete structures like words and labels. So for now, I'm just gonna present indicator features in the context of a simpler feature function that represents an input sequence, a certain position t, and a label we're trying to assign in there. So what I change here is that I'm not using the previous predictions, then I will add them. Okay, so what is this f function? Well, it's a function that, given these values, computes a representation of this candidate assignment. And it does so in the feature, so you can think that the return of this function is this vector, okay, that has the features. Each feature is a value. So what is one particular feature? Okay, so you might think of coordinate j. You might think that with each coordinate we associate a function that computes a certain value. Okay, so we have different functions that each looking at specific properties. So what is that these functions look at? Well, so just looking at the signature of the function. So anything that we can compute using the full sequence, the position, and the label, in principle, can be used as a feature, okay? But because our goal is to compute these scores that tell whether a label is correct or not, so what we should do in practice to make the model successful is to encode anything that can indicate whether label L is or is not a good label for that position of the sequence. Okay, so in practice, that's the notion of feature. What is an indicator feature? An indicator feature is a feature that the target value is binary. It's either 0 or 1. So they look at a specific property, and the value is 1 if that property occurs in our decision, or 0 otherwise. So for example, we might set up the jth coordinate to be 1 if the current word is London and the current label we're trying to assign is location. Okay, so this feature will encode that we're observing an output label log location assigned to London. Okay, so in principle, because the word London tends to be a location, so the parameter associated with this feature, we can put a positive value, because in principle, we want assignments of type location to words that are London, because London is a location, right? But we might have another feature, say dimension k, that the value is 1 if the next word, so at position t, we look at xt plus 1, so the next word is went, and the candidate label is location. Okay, so this is the case for the example, Jack London went to London. Okay, went to Paris. Okay, Jack London went to Paris. So if the next word is went, whenever we have a word, we're trying to assign a location label, and the next word is went, it is actually unlikely that it's a location, right? Because locations, so if the next word is went, it means that the word is in the subject position. Okay, so locations don't tend to move, don't tend to go anywhere. So this small pattern might be indicative that this is actually a wrong assignment. Okay, so if we have this feature, we're letting our model put a negative weight here in order to compensate that, yes, when I see London, it is a location, positive weight, but if this assignment, the next word is went, I might put negative weight to make the sum of weights to be maybe negative, okay, if we're assigning London to location and the next word is went, okay? So if we have these kind of features, we're giving the model the expressivity to combine labels that we are trying to assign with certain patterns of features of the input, right? And by giving this expressivity and letting the algorithm adjust the weights, our hope is that we can end up with a good classification, okay? So now, because these patterns behind each coordinate just look at a specific word and with a specific label, you can think that in order for the model to scale to the English language, okay, it needs features for each word and features for each label and surrounding label and surrounding words and so on. So the dimensionality of these feature spaces is going to be huge, but then it's going to be sparse. Only a few dimensions of this vector will actually be active. Okay, so whenever we use indicator features as opposed to neural models, when we use indicator features, we have this property that the representations are very high dimensional but very sparse. So you might be asking, well, you are posing here a learning problem, and you're telling that these features are constructed manually, and so really we need to set up functions like that look at specific words with the specific labels, because it looks like if we need to set up these functions manually, it's like we're putting a lot of prior knowledge about which words should be in the features. Even if the final weight is adjusted, just understanding which features, which words should participate in here, it seems like a lot of work. So no, this is not done like that. This is done with what is called feature templates. So feature template is a generalization of just a particular feature that generates a lot of such features. Okay, so it's a pattern template that once instantiated creates those features. Okay, so let me just give a quick overview of that. Okay, so a feature template is a mechanism to generate many indicator features. So we define a feature template by a certain type and a number of values, such that the instantiation of a template with such values actually gives actual dimensions. Okay, so the feature I was discussing this before, for example, the corresponding template could be as follows. Okay, the parameters of the template, I'm calling this the word template, and the parameters are a certain label and a certain word. Okay, and then I'm writing a function such that given the input, if the input, if the word at position T is the word of the instance of the template, and the label is the label, then this the value is 1, and otherwise it is 0. Okay. So this type of feature template is identified by this tuple: the type, a certain label, and a certain word. So instantiating labels and words provides a number of actual features. Okay, so for example, here, say that our vocabulary are words I, you, went, so, John, Mary, London, Paris, and that our labels are nothing, person, location. So if we put all combinations here, we get a feature vector associated to this template. So this template with these labels and these words generates all these dimensions. Okay. Now, if we put a certain value here of a sentence, a certain position and a label, this will pick which word and label are we instantiating. Okay. So actually, we could think that our feature vector, like this diagram shows, the features are actually indexed by these tuples, and the weight vectors are also indexed by these tuples. So actually, the weights of a certain model are associated with these tuples. Like, for example, this tuple here corresponds to having the pattern of the word John with label person, while this one here is the weight associated to having John with label location. Okay, so if it's possible that John has a location assignment because maybe there's some place called John something, so then maybe this has positive weight. But if it's completely impossible that the word John is labeled as location, then this could be negative. Okay, and so this is the type of expressivity that the actual model has. Okay, the model has a weight for each such feature. So how do we actually create feature vectors and weight vectors for state-of-the-art systems that actually work with feature templates as opposed to representational learning? So as I said, it's not that we're creating the dimensions manually. What we do specify manually when designing a system are the feature templates. Okay, so this is something I need to specify. And then, given a certain template, I will instantiate the parameters of the template to all observed values on the training data. And so for every value, I will get the corresponding dimension in my model weights. And so, as I said before, because these are discrete patterns looking at combinations of words and output labels, so this will generate a very sparse, high dimensional feature space. Okay, so the weight vector is going to be indexed by the same coordinates. And so most features, the important point is that this way of constructing features generates a massive amount of features, and most of which are completely irrelevant for the task at hand. That's not really a problem, because what this approach relies on is that the learning algorithm will choose what are the relevant features. Okay, so one important aspect that made feature-based models successful was that the manual work of specifying features only needs to identify classes of features that include the relevant one. It is not a problem if we create features that are completely irrelevant. What matters is that we create a large number of features that include the relevant ones without prior knowledge about that. And so the learning algorithm, when estimating the parameters, will be able to set a weight of 0 to the features that are completely irrelevant, and to put positive or negative weights to features that are relevant, with the goal of making the classifications correct. So in the context, for example, of name entity extraction, I mentioned that before. So features that are very relevant. So if we're thinking about this as a classification problem, okay, without just looking at predicting one label at a time. So the current word is very relevant, as we saw in the example template. Capitalization information, whether the current word is capitalized or not, whether it has digits, whether it has prefixes, certain prefixes or suffixes, whether it's a known location, we can encode this as a feature. So these are features of the word itself, right? So all these features about capitalization and suffixes allow us to generalize to name entity words that we've never seen, that do not appear in the data, right? While it is also important to encode the context, the surrounding words to the position of this decision by encoding the next word, the previous word, etc., etc. So in practice, we construct the templates by first deciding, okay, what are the relevant patterns of the input alone, of the words alone, and the context. And then for a number of patterns, we combine this with every possible label of our signature here, and then we instantiate that. So typically, looking at this diagram, this represents a super high dimensional vector. We can see that this vector of features, or the corresponding vector of parameters, we can identify blocks, okay? So for each label, we can identify the corresponding block, okay? And then inside each block, so all these are the parameters related to location or to person, but then they all have a similar structure, okay? A number of features look at the current word, a number of features look at capitalization and digits, prefixes and suffixes and so on. So each pattern here, together with its label, generates a subblock of parameters associated with these properties. So and now, if instead of having a simple multi-class classifier to predict labels, we have this greedy model, okay, where now, in addition to the label we're assigning to position T, we also have the previously predicted labels, okay? So the way this goes is that just our feature templates now can look at richer things, okay? So for example, we can look at, we can have templates that look at 2 labels at a time, okay? So this can look at a certain word, at the current word, the previous label, and the next label, okay? So this template is extracting the 2 labels together with the current word, okay? So in practice, if we have a sequence of labels, the preceding labels here, how can we represent these as templates? Actually, it's always challenging to represent sequences in the form of templates. So the new trend is to use representational learning, you know, some form of BiLSTM that computes an embedding of prefixes, okay? But we can also do a similar representation using templates. So in practice, we would have feature templates that look at the labels that are next to position T, like this, okay? So this is looking at the previous label alone of all these prefix. It's only looking at the label of T-1, just creating a bigram here of labels. We can look at what labels exist in here, or we can combine the previous labels with words and other features, okay? So as I said, neural networks automatically induce very good representations of these structures, okay? And I think it's been a clear success. There is not a need to do this engineering of deciding feature templates, but that doesn't mean that it's not useful to think about, when we think about models. I think it's still useful to be able to imagine feature spaces where actually the parameters related to that feature space are observable quantities, okay? Because then if we learn a model and recover what are the most important weights learned by the model, then we can directly associate the weight with certain patterns, okay? So we can, after learning, we can decide what words and what combinations of labels are actually important for this model, right? While with representation learning, this is a lot more difficult to do this interpretation, okay? But it also, I want also to highlight this construction of feature templates, because this gives a strong intuition of what neural models might be doing, okay? So they're doing these things automatically. They're representing each of the values of this complex structure here that we're trying to represent. So what neural networks are doing is take each of the possible values and somehow consider all possible combinations of this, and figure out during learning which of the combinations have a good effect to minimize the loss of the model, right? So if we can do, if we can go very far by doing it manually, and we give the same type of expressivity to an algorithm that is able to construct a lot more combinations automatically, it's no surprise that if the optimizer doesn't get stuck, it's no surprise that the algorithm can do a lot better because it can try a lot more combinations, okay? But what is essential is that the relevant information is somehow in this decision context, okay? And this is the point of this lecture, okay? How can we predict structures knowing that it's just impossible to encode the full output structure in one go? So we need to break down somehow the representation of input-output patterns into different ways, okay? So in greedy sequence prediction, what we do is to construct incrementally, having access to the previous levels. Later, I'm going to discuss this in the context of factor model, which is a different approach to structure prediction. But before that, I wanted to comment that this greedy model that keeps doing one prediction at a time actually can be thought, I think it's very intuitive, one prediction at a time, okay? But there's a family of models, which I'm calling here transition systems. It has different names. There's a sequence of states and a sequence of actions, And the structure we're predicting is built incrementally using this sequence of decisions. Okay, so so how it works is that there's a set of states, and there's an initial state and a final state. Okay, so the process. So I'm just going to describe this at a very high level way. So we have a certain input, say a sequence, and we're trying to predict an output sequence. So the system is always at a certain state. Initially, we are at the initial state, okay, and then we keep transitioning from one state to another until we reach one of the final states, okay, at that process. So final states encode the situation where the output structure is completed, okay, and so at each state, so the model specifies a set of actions that we can take given the input and a certain state. It specifies a set of actions for all the possible states. And so what we do at a certain state is to pick a certain action, and here's where the model takes place. Okay, there's a scoring function that given the input, the current state, and a certain action, okay, it computes the score of that. So we're gonna choose the best action in this context, and then there's a transition function that given a certain state and an action that we pick, move to the next state. Okay, and so on until we finish. So very briefly, so in greedy sequence prediction, the input is a sequence, and the states, let's say, are the prefixes from left to right of the output sequence. Okay, say that each prefix of output labels is a possible state. Okay, so we start with the initial state, which is the empty output sequence. Okay, and so we're gonna loop here until we reach a final state, which means that this state is encoding an output sequence that is complete, that is of the same length. And the actions are very simple. At any point, the actions is just adding one more label. Okay, so there's an action for each possible label. Okay, so if we instantiate this, we'll get the greedy model I was talking about in the context of a sentence and a certain position. Okay, there is an action we're considering, the next label, given the previous labels which are in the state. Okay, and so transitioning is just adding this label to the current state. Okay, as I said, I'm not gonna give details about that. But I want to comment, so transition systems are very successful in NLP. They are simple. They're very fast because this just runs in linear time, okay? And they're very expressive in the sense that these states are typically very rich. They encode the structure built so far, and so this is very powerful. So, you know, I showed greedy sequence prediction. There's shift-reduced, so for syntactic parsing, there's shift-reduced approaches, which essentially are also transition systems. And in the parsing literature, that's full of these methods for parsing. There's also word segmentation, machine translation. All these problems can be framed as transition systems, okay? Or better said, there's transition systems that perform very well for these models, especially with the use of deep learning these days. Transition systems are very successful, okay? Because these scoring functions can be learned with neural networks, and so you train the network to perform this correctly. Okay, still the neural network is operating on top of a pre-specified transition system of this sort. Okay, so the neural network is learning this kind of scoring function as opposed to just doing a linear approach where we supply features and learn the weights. Okay, this is the schema. And one problem of this type of systems is that the predictions are greedy. Okay. And so what does this mean, that predictions are greedy? So greedy predictions don't follow any notion of optimality, okay? And so they're prone to search errors. By search error, I mean that if a decision is done, we cannot undo it, okay, at a later stage. So let me show, so what might happen here, and this thing has been the topic of a lot of research in structural prediction, is the scenario. One can think of a scenario where maybe the model, our scoring function might be right at the global scope. If we look at all the sequences, it might be right at the global scope. That doesn't mean that it's perfect at every local step, okay? So let me show you an example. What do I mean by that, or what might happen? So say I have this sentence here, and I have the possible assignments of this for each word, okay, the possible labels. So as I said in the very beginning, choosing a solution here is a solution is a path, okay? So you might think of a greedy approach as an approach that first chooses one label. It's building the path incrementally in a greedy fashion. So it chooses one label and then chooses which of the next label is most appropriate, and then it keeps going, okay? So say that I'm at this position here, okay? And I'm asking the model, okay, what's the best label I can assign to Paris, okay? So I run the scoring, this is all invented, okay? But I run the score function and say, well, Paris is certainly not a dash, the label, so it gives -5, but it might be a person with 5 points and maybe a location with 10 points, okay? So for some reason, at this point, I saw Paris looks like a city name, and so the model gives 10 points to this label using all this context, okay? And so if we do a fully greedy approach, we're at this position here, and from this position and this is a mistake, from this position we ask the model, okay, what comes next, okay? So then going from location to location gives a -5, okay, because Jackson doesn't look like a location at all. And going, now labeling Jackson as person, it's -10 points, because kind of switching with adjacent words, switching labels looks like really bad. So for some reason, the two assignments of Paris here look good, +5, +10, but from this point, the assignments that can be done from here are all bad, okay, in such a way that if you are here, there's no way you can recover that, okay? So that's what I mean, that the model might be right at the global scope, but not at each greedy step, because if we take that, if we set up a notion of global optimality and say, okay, I want the sequence that maximizes the sum of scores, okay? So if we had taken this path here, we get +5 and +10, we get 15 points for this assignment, while here, there's no way, we get 10 points here, but then we only get negative, okay? So we never get to 15 points. So this is what we mean by, at the larger scope, there's the notion of globality, and it might be that the model is right, okay? The scoring is not bad, but this is more of a search error, okay? We took the wrong decision, okay? So in general, if the scoring depends from the very beginning, there's not much one can do. There is a solution. There's a schema called beam search. It's a general, I'm sure that many of you are familiar with that. Okay, it's not just a search process for machine learning. It's a popular search method, local search method in AI and computer science. So instead, greedy prediction, we can think of maintaining just one hypothesis and keep incrementing that. Well, so if we want to be a little bit more robust to search errors, instead of maintaining one path, we can maintain several paths that look good, okay? And these several, so we need to define some computational budget. So we know that the full set of paths is exponential. We cannot explore all of them, but we can explore more than one, or even more than 10, or more than 1,000, okay? So you can really scale this thing up. And of course, the more paths you consider, so if in this case we consider 2 paths, so maybe the 2 paths would end here, and we would try both. And maybe when we arrive here, we see that the most promising path is the one that goes through these assignments, not the other one. Okay, so maybe if by doing beam search with 2 paths, this toy problem would already be solved. Okay, so beam search is successful. It's a way to improve greedy predictions, and it's common that transition-based systems work in conjunction with beam search. I'm not going to describe beam search in more detail. Actually, the actual strategy sometimes is specific to the task and the type of transition system, okay? But as I said, empirically, it is often the case that beam search improves over greedy search, which means whenever a paper shows that this is the case, that beam search improves over greedy search, it is a case where the model is not that bad, but it was a search error. Maintaining just one hypothesis is not robust at all. So this is all for transition systems.
Hello. I think we covered the first hour.
Yeah.
There's been 10 questions, very good questions in the Q&A chat. I hope you're enjoying.
I don't know if there are any more right now.
Yeah.
So if people want to.
I must say that my lecture is a bit heavy on notation. It's a bit more of my style. I'm sorry about that. There is some notation, a lot of notation for the feature engineering. It's not needed. Okay, to move on. But the point was that to show that that these models somehow the parameters need to be associated to some form of representation of vector that combines together a part of the input and a part of the output. Okay, so the feature templates are a very simple way, an engineering trick to generate those, or you can use, these days people use deep learning. These things can be combined. There's been questions about that. I cannot give you I don't think there's a general recipe on how to do that, but you can check papers, especially at the beginning of neural networks. Back in 2015, we were all reluctant to just jump into deep learned representations. So there was a lot more work on trying to combine feature templates that were working very well with word embeddings and things like that. And now people seem to learn. I would actually challenge, and I don't think that deep learning doesn't always improve. Okay, in many cases, a simple set of templates will do as good as as very complex and heavy and expensive and energy consuming large representation. I would encourage you to try one of these. But in any case, that's research. Okay, that's the empirical part of NLP. And I think it's kind of useful to know that these simple representations exist. In any case, if there's questions, please use the chat, the Q&A chat, and I'll be happy to answer, okay?
So maybe I guess we can do a small break. I don't know. So it's 10:05. We get back at 10, 5 minutes. Do you think this is enough, Fernando?
Maybe 5-10 minutes.
A bit more. Okay, so back at 10:15.
We will accumulate delay then. I think it's good to breathe and drink some water, but there will be the half-an-hour break later, right?
Yeah.
Okay.
No, there no be. We won't have this half-an-hour break, right?
Okay. You want to distribute it? Okay.
Yeah. Why? Because we have 3 parts, and you want to then distribute the break between. Okay. Yeah.
Okay. So let's do that.
Okay. 10 minutes, right?
10 minutes from now.
Okay.
Yeah. Okay.
See you later.
See you.
So now I'm going to discuss factored sequence prediction. Okay, one main difference with greedy prediction is that here we view our output sequence as a set of factors that overlap. So in this example, I'm using a bigram factorization where the output sequence is seen as this set of bigrams of the output. Okay, adjacent labels, any two adjacent labels of the output is a factor. Okay, so the scoring function of our model will produce a score for each factor of a solution. That's one main difference. Okay, this limited view on a part of our output structure. A second difference with greedy prediction is that now we have this notion of global optimality. Okay, so given a certain candidate output sequence, we're going to score it as the sum of scores on the factors, and then we'd like our decision function, our structured predictor, will pick the complete sequence that maximizes this score. Okay, so implicitly, we want to select this output sequence. The main advantage of working with factored representations is that this computation, we can do it very efficiently. Okay, so I want to discuss two main aspects of this family of model. One has to do with representations, and in particular, with the fact that in case that our scoring function is a linear function, then we can view the structure predictor as a global linear model for sequence prediction. The second aspect I'm going to discuss is the methods by which we can recover the argmax solution in an exact fashion. So starting with representations, features, and scorings. So if our score function is linear, it means essentially that there's a weight, the parameters of the model are this weight vector W, and then we have a feature function that represents a certain bigram of the output in a certain position in the context of a sentence. Okay, so this essentially can be done using similar methods as before, using feature templates. Okay, or in principle, any representation should work. Okay, so I'm not going to discuss in detail how we do this in factor sequence prediction. As a matter of fact, if we look at the feature template function that I gave for greedy models, one can this particular definition only looks at two labels at a time. Okay, so we could actually use this kind of template for factor models. Okay, this template is possible under greedy prediction, but also under factor models. So what I want to show now. So let's assume that we have already provided a function that for any bigram at a certain position, it gives us a d-dimensional vector. Okay, and in the case that our features are indicator features, namely 0 or 1, so each dimension is a Boolean indicator, 0 or 1, maybe showing whether this pattern here, person, person, and London, occurs in a certain bigram at a certain position. So now this is defined at the level of bigrams at a certain position. So now let me define a new function, which is a feature representation of a complete input and output sequence. Okay, while here I'm codifying a bigram in a certain position, this function will produce a feature representation for the two sequences at once. So in principle, it's not obvious how to encode sequences that can be arbitrarily long into a feature vector of fixed dimensionality, but there's a simple way to do so. So if we do have a function at the bigram level, I'm going to define this function at the global level by summing at each position. So y is given. So I'm going to consider each position 1 to n. Obviously, n is the length of these sequences. And I'm going to consider the feature vector that results from evaluating this function at position I with the corresponding bigrams taken from here. Okay, so I get one feature vector for every position, and I just sum them. Okay, so summing d-dimensional feature vectors in a certain space gives us a d-dimensional feature vector of the same space, in the same feature space. Okay, while a single vector here is encoding one bigram at a certain position, the sum is encoding, let's say, a bag of bigrams at all the positions, back of all the bigrams in this output sequence at all the positions. Okay, so we can consider this as an aggregated representation by summing bigram feature vectors. Okay, so again with the analogy of bag of words or bag of bigram patterns. So if here one dimension is a Boolean indicator, a 0 or 1, so here after summing it's going to be a count, right? So while this is flagging the occurrence of a certain pattern, this is counting the number of times this pattern is in our input-output structures. Okay, so why am I defining this vector? So I'm going to call this a local feature representation, and I'm going to call this a global one, namely global because it's at the global level of two sequences. So this is nice to define because if we put it back together, okay, we can frame a structured prediction with linear models as just any, as in the general form of linear models, namely that in linear models, given X, we want to predict a Y, and we're going to pick the Y out of all possible Ys that maximizes a linear product between a weight vector and the feature representation of this Y. Okay, so if you take a multi-class classification, it's written exactly like this. Okay, the difference is that in multi-class, these Y values range over each possible label, while here the Ys range over each possible full output sequence. Okay, irrespective whether we can enumerate this space or not, which we can't in structured prediction, this is exponential, irrespective of the cardinality of the output space, the form of the score, a linear one, is exactly the same. Okay, but in addition, for factor models, I'm going to say that this representation actually corresponds to the sum of feature representations at the bigram level. Okay, so this is not the linearity of this expression. Okay, I'm saying that in this family of models, the score of a pair X, Y has this linear form. Okay, I can just write down the definition of F, and because it's linear, I can put the weight vector inside. And so I can see this score as a sum of scores. Okay, so this very simple linearity gives us two views of linear factor structure prediction that are very useful. Okay, so when it comes to reasoning about learning the weights, it's going to be very useful to know that our model actually follows this form, because many of the techniques for learning linear models, and maybe nonlinear models too, make use of these forms. Okay, just a product between weights and feature representations. Okay, so we're going to try to set up the weights such that the score is performs well in terms of this decision function. Okay, so it is very easy to reason about linear models using this form. Now, when it comes to computations, namely having to pick the right Y for a fixed W, it's going to be useful to think about this form. Okay, because here it's saying that the score is essentially this is saying that our model is essentially scoring each part, each bigram in a sequence. And so the score of a full sequence is the sum of scores. And as we will see next, this is the key to be able to solve this argmax problem in an efficient way. So now we're going to cover the question of how to make predictions with factored sequence models. Okay, and so since the goal here is to make predictions, I'm going to assume two things. First, that we have a model that where the features are already defined and where the weights are already learned. Okay, later in the class, we're going to see learning algorithms to estimate the weight and its prediction. So I'm going to also assume that I have a certain input sequence. Okay, so what I want to focus on now is how to solve this equation, how to choose the complete output sequence that satisfies that it's the maximum of the sum of scores at the bigram level. So the main result here is that the Viterbi algorithm can solve this problem in linear time in the length of the sequence times quadratic time in the number of symbols of our output alphabet. Okay, the number of labels that we have in our output sequence. So this degree here, it's quadratic. It's quadratic because we're taking two labels at a time. Okay, if we were considering a a factored model that considers 3 labels at a time, then this exponent here would be 3. So now, in the next few slides, I'm going to describe the Viterbi algorithm. Okay, I'm going to do that at a high level, trying to highlight the intuitions behind these scoring functions and the algorithm. I'm not going to give a complete justification of why these algorithms work, but in any case, there's a lot of literature. So my main goal here is to actually establish that this is the case, that for factor models, we have efficient algorithms that can recover the argmax in an exact fashion. Okay, there's no search errors here, and give you some intuitions such that then you can study the Viterbi algorithm in more detail. So let's get started. Because the model is fixed and also the input here is fixed, we're just focusing on the prediction for a particular example. So I'm going to change notation because I need to make use of these scores. Okay, so I'm gonna assume I'm just gonna redefine this like that. Okay, so S of I, A, and B is the score of at position I of bigram AB. Okay. So we're trying, given that I have these scores, and you can really imagine that I have a table with all these scores, okay? That's the input to the algorithm, a table with all these scores. And I want a routine that finds the maximization, that sequence that maximizes the sum of these scores, okay? So before getting into how to do this maximization, how to recover the argmax sequence, let's think a little bit more about what does it mean, this factorization, okay? And to do so, consider just this simple example. Okay, Jack London went to Paris before visiting London. So this is meant to be, let's say, a long sentence. Okay, and let's consider this solution here. Jack London, where London is laid incorrectly as location, went to Paris before visiting this one. Okay, so we have a possible sequence of output labels, a complete one, and then I'm calling Y, and then I have another sequence Y prime that just differs in one label. Okay, so these two are just the same except for one label. Okay, so the question is, if we are scoring sequences in this way, what is the score of Y prime relative to the score of Y? Okay, so say I want to compute this score, and someone already gives me the score of X and Y. So so there's a simple expression where I can compute the score of this output just from the score of the previous output, and that's because there's only a difference. Okay, so because we're factorizing like that, all the scoring around here doesn't affect the scoring around here. Okay, there's no dependencies in the scoring function. Okay, so as a matter of fact, if I'm only changing one label, then and I have a factorization of order 2, then only 2 bigrams are going to be affected, okay? Namely, the bigram at position 2, taking these 2 labels, and the bigram at position 3, okay? So what we have is that the score of Y prime is the score of Y plus, we consider position 2, the score of person minus the score of person location, plus, at position 3, the score of person nothing minus the score of location nothing. Okay, so one change, if we want to consider, if we have a running solution and we want to make one change, we only need to look at the bigrams affected by this change. We don't need to look anywhere else. So this is in contrast with, for example, greedy models. Okay, so if I have a greedy model that has predicted, if a greedy model has predicted this sequence and I want to make a change, okay, the value here, it's going to affect the predictions of the upcoming labels, okay? Because the upcoming labels look at all the previous decisions, okay? With this factorization, this does not happen. So another way to see that is that if 2 output sequences share a lot of bigrams, okay, the scores of these bigrams are also shared. So this would suggest that I could start with a certain solution and then try to make small changes and see if I improve, okay? This could be one way to go. But actually, Viterbi this allows for many different strategies, and this allows for an incremental construction where we always keep the optimal sequences up to a certain level. Okay, and so this is the main idea behind the Viterbi algorithm. So Viterbi is a dynamic programming algorithm that uses a recurrence based on building the best sequence incrementally from left to right. And it does in an exact fashion using a recurrence. And the recurrence is as follows, okay? That's an assumption of the recurrence, is that at any position I of the sequence, and for every label in our label set of tags, we have access to the best subsequence from position 1 to I that ends with label L. So let me explain what this means. So take label person as an example and consider the position I, okay? So this is a sequence of labels with one label for every position between 1 and I. And the tag at position I, the label at position I is person, okay? So out of all possible subsequences that end with person, this one is the best, namely is the subsequence that maximizes the sum of bigram scores in within, okay? So the assumption is that at a certain position, for every label, person, location, and dash, I do have the corresponding best subsequence ending with the corresponding tag, okay? And the recurrence is that if I have these subsequences for position I can very easily compute the same type of subsequences for position I plus 1. Okay, so I'm gonna extend these subsequences by one step, okay? So what, in essence, what the algorithm is asking is, given that I have this now, what is the best sequence up to position I plus 1 that say ends with the tag location, okay? So what would be the sequence ending with location? This could be anything that ends to this position. So the main observation is that the best sequence up to position I plus 1 has to be made with the best, one of the best subsequences up to position I, okay? So one of these, this needs to be made of one of these, okay? And obviously augmenting with a new tag, okay? So since here we're asking for the subsequences that ends with the location, so we know the tag that goes here. So all we need to choose is which of the three previous subsequences is the best to come to this point, okay? Now, if we consider, say that we consider this, okay? If we add a location tag in here, we know that the score of this sequence up to position I plus 1 is the score up to this position plus a bigram score, okay? And the same for location, with the location score, with the location score, and the same with dash location score. Okay, so the best sequence here is one of these three, and so if I have access to this, then it's just linear in the number of labels. Okay, computing this subsequence up to position I plus 1 is linear in the number of labels, given that I have the best subsequence up to position I. Why the best sequence up to a certain position is made out of one of the best sequences up to the previous position. This is the essence behind this algorithm, and I'm not going to show a formal proof, but this is the typical proof by contradiction. Okay, so say that the best sequence up to this point is made, maybe it comes from here, but is made of some other subsequence that is not the optimal up to this point. Say that this is the case, okay? Then, because of the intuition we saw before that I can replace replace bigrams and just recompute scores, okay? So if I do changes here, this will not affect the score here, okay? So if there exists a better subsequences that ends with location, okay, I could replace it and obtain a better sequence, okay? So it wouldn't be the best, okay? So because of this, because the score in this area only depends on this tag here and doesn't depend on the tags that are selected in this portion, then it has to be the case that the best subsequences to each position are made of best subsequences up to the previous, okay? Because we have this independence of scoring. So this is in essence the main idea behind Viterbi, okay? The ability to keep augmenting these subsequences. So we can write the algorithm in many different ways. So here's a very compact description of the algorithm in declarative form. It's basically the recursions written with equations. So I'm going to try to be quick at this, even though it's not my purpose that you completely follow these equations. I think that it's much better that to get convinced that Viterbi works, it's much better to see detailed material on that. work it out, especially then prove it mathematically, the recursion, then try it out on some examples and possibly code it. There's different ways to code it too, okay? So I think that by exercising on the algorithm, you'll get the idea of what are these recursions, okay? But very quickly, so the problem statement here is that I want to recover a sequence of labels of length n, okay? Where each sequence, I want to recover the maximum sequence of length n, where the score of a sequence is factorized in this way, okay? There's a score for every edge, there's a score for every pair of adjacent labels. And so what I'm going to do is to break down into subproblems, okay? And we'll have for every position I from 1 to n, and every label, I will have one subproblem, okay? I'm calling this delta, okay? One thing is changing, I'm doing here, is that the subproblem is not going to be about the argmax, it's going to be just about the score, okay? And so this subproblem is, the scoring is pretty much the same, but it operates on prefixes of sequences. So I'm asking here, delta IA is asking for what is the maximum score of any sequence from position 1 to I that ends with A, okay? This is what this notation means. It's a prefix of sequences of length I ending in A, and the scoring is the same as in this one, okay? So it turns out that if I define all these problems, okay, for each position and each label, okay, I can solve all of them in a recursive fashion, namely the base case where the position is 1, I'm just asking for what is the score of a sequence of length 1, okay? So my model, well, here there's some notational conventions to indicate that essentially this is scoring a sequence of just one label, label A, okay? So I have a special symbol to denote that this is not a pair of symbols, but just one, because the previous symbol just doesn't exist at the beginning, okay? This is just a convention. So if we're talking about sequences of length 1, it's just the base case. If we're talking about subsequences of length more than 1, okay, then there's the recursion, okay? So it has to be that the best sequence up to position I ending with A, it's the combination of the best sequence of the previous position, delta I minus 1, augmented with the bigram, okay? So we need to loop over every possible label and then augment the bigram, okay? So so if we solved the delta problems at I minus 1, we can now solve the problems at delta I only looping through the symbols. So, okay, so where is the best solution? Okay, the best solution is found at position n, okay, which is the initial length of the sequence, and we need to loop over A's. This is more of a technicality. But if we solve, and the other technicality is, if we solve the max, how do we actually recover the sequence, not the argument, okay? I'm not going to describe that, but this is done through what is called back pointers, okay? So essentially, what is this? So when we're solving all these problems, there is a trace of the computation, namely, what is this, when we are solving this recursion, okay, what is the symbol here that gave the maximization, okay? That gave the maximizing value, okay? So in an implementation of these recursions, we need to keep track of which of the symbols gave the max value, okay? And that's what we call back pointers, okay? So it can be recovered. I'm not gonna give details, just believe me that this is possible, and then please go ahead and check the more detailed materials, or even, as I said, try to code these in different ways and convince yourself that this can be done, okay? What matters here is the cost, okay? It's not, even though it's searching over an exponential number of sequences, the cost is linear on the length and quadratic on the number of labels, okay? It's linear because there's linear number of these problems, okay? There's one problem for every position, and it's quadratic because there's one problem for every label, but to solve each of the problems, we need to loop over labels, okay? So the quadratic dependence is on this, okay? For every A, we need to loop over B. So for every position, we need to do quadratic work in terms of the number of labels, okay? This explains the cost. One thing I'd like to point is that on the one hand, factor models that score solutions like this are not directional, okay? There's no direction. Factor model just considers the parts of a certain candidate full sequence, and they score each of them, okay? But there's no direction that I first score the first one and then the latest one, okay? In greedy models, there is an established direction with the model, but in factor models, there's no direction, okay? However, this Viterbi algorithm works from left to right, okay? So as homework, I propose you to rethink of this dynamic program and to rethink of these equations and rewrite it such that the algorithm, instead of proceeding left to right, it proceeds right to left, okay? So the point of this exercise, so for one thing, it will help you get familiar with this recursion, but importantly, if it turns out that this is possible, which it is, okay, it's going to be an indication that the underlying model is not directional, okay? The algorithm that computes the best sequence, it is directional, but for the same model, we can either compute left to right, right to left, or actually there would be also variations where you start from the middle and augment it. That would be possible. It would be weird and possible. Okay, but the algorithm is directional because it builds the sequence, but the model is not. Okay. In contrast, with greedy models, if the features look at the previous labels, then the algorithm needs to profit left to right. If we want a right to left model or process, then both the prediction algorithm and the model need to be in accordance. Okay. Okay. So Viterbi is actually a very general algorithm, and also an algorithm that applies to lots of cases. Okay. So so what I described is just a high-level view of Viterbi, of the recursions. Okay. But then there's a number of situations where we do variations of Viterbi. Okay. So I'm going to comment 4 without going into much detail. So the first scenario is the sparse Viterbi, okay, which applies when only a few labels apply to every position, okay. So in what I'm discussing today, I'm assuming that there is no such prior knowledge, okay. So at every position, we just try every possible label. But in, for example, in part of speech tagging, okay, where we try to guess the syntactic function of words, typical data sets include 10, 50, or even 100 possible paragraph speech tags. Okay, the label set is pretty much big, even though we have dictionaries that for every word ahead of time we know what are the possible paragraph speech tags, and it turns out that most words cannot have any paragraph speech tag. Okay, so the ambiguity of either words are not ambiguous, meaning that only one is possible, or maybe there's an ambiguity over 3 or 4 labels, but not all of them. Okay, so this is a case where only a few labels apply to a certain position. Okay, this is prior knowledge. Okay, by the symbol we have in a certain position, we know by using a dictionary that only a few apply. Okay. Another possibility, which is also common in many problems, is that ahead of time we know that not all bigrams are possible. Okay, only a few of them are actually possible, okay, because we disallow certain combinations of adjacent labels. Okay, this is all prior knowledge that we have compiled in different ways. It can be a dictionary, it can be some form of automata, it can be a grammar. Okay, so then in this case, one needs a sparse implementation of Viterbi. Okay, and the sparse implementation will have an effect on the quadratic cost of the factor. Okay, the recursions I showed before point to its linear time times the quadratic term on the number of labels. Okay, so if this label set is 100, then the quadratic term over 100 is a lot. Okay, but if in practice the number of possible labels is much smaller, let's say 3 or 4, then the sparse Viterbi will cut. Okay, will cut the cost on this. Okay, so please check. There's literature on how to implement sparse Viterbi. So please check it out, because it's actually for NLP, it's very relevant, okay? Because NLP is an area of problem where most likely the output space is sparse. Not every part of output can be assigned to every part of the input. Another variation, which I think I already mentioned, is instead of working with bigrams, we can extend the order of the factors to consider higher order Viterbi. Okay, so one example would be we want to factorize at trigram level instead of bigram level. Okay, so in that case, the cost, if we factorize at trigrams with 3 symbols, then this exponent is 3. Okay, so essentially, for this type of sequence prediction, the number of tags we have in a factor is going to be the exponent. Okay, this is very common in post tagging to run at the trigram level, and so the best methods that that are trigram taggers for parameter tagging typically typically use the sparse Viterbi. Okay, so when you go higher order, there's more chances that you are not going to allow all possible factors. Okay, so in order, these two techniques are commonly combined. As a matter of fact, sparse Viterbi is a requirement to make higher order predictions tractable. Okay. Okay, this has to do with the costs of Viterbi or how we apply it. Another variation that is very common is k-best Viterbi. It's on a different axis. Okay, so in the Viterbi I presented, we're asking for the one best sequence. Okay, we want the sequence that has the maximum score. Okay, in many cases, instead of the best sequence, we want more than we want the top best. Okay, the k-best. So instead of so if k is 1, it's the previous specification. But in many times, as I said, we want the 10 top scored solutions, or maybe 100 or 1,000. Okay. So in k-best Viterbi, instead of computing the best sequence, we return the k-best. Okay, not just a single best. And so at the very beginning, I commented 4 approaches to structure prediction. The latest one was actually re-ranking. For re-ranking, applies a scoring function at the global level, and it relies on having, instead of working on the full set of possible outputs, it works on a reduced set of outputs. So precisely to compute that, we use a more simple model, like a factorial model, and we run k-best Viterbi, or it's also called k-best inference in general, to recover, let's say, the most likely 1,000 solutions, and the re-ranking applies on top of that. Okay? And the last variation, which is also very common in the context of machine learning of this type of models, is a forward-backward, okay, which is the Viterbi for sum product computations. And that, let me extend this. So forward-backward max sum computations, okay? The Viterbi algorithm I presented solves a max sum recurrence, okay? What does it mean? It means that each sequence is scored in terms of a sum of the scores, and then we're asking for the maximization one. So we're doing a max over sums, okay? Another common specification of computation is the sum product one, okay, where the aggregation of scores in a sequence now is a product. We're making products of scores, and then instead of asking for the max, we're asking for the sum. So we'd like to compute, we would like to consider all possible sequences. Then for each sequence, consider the product of the scores of its bigrams, and then we'd like to sum all these scores of sequences. Okay. In a few slides, when I talk about log linear models, I will motivate why we would like to have this computation. Okay. What I want to highlight here is that the same style of dynamic programming also works, and this is exactly the same that than what Noah Smith showed in the lecture of HMMs about Viterbi and semi-ring generalizations. Okay, so here I'm changing the semi-ring. So whenever we use Viterbi for sum product computations, it's not called Viterbi anymore, it's called the forward algorithm. But as I said, the type of dynamic programming is the same, okay? And it proceeds by also defining sub-problems, okay? We're trying to solve this problem for sequences of length n. And what we're going to define are forward quantities, which are the sub-problems, namely, I'm calling this alpha, okay? Alpha IA, okay, is the sum for sequences up to position I of all the sequences that end with tag A, okay? And for each of such sequences, I'm going to consider the product of scores, okay? So here, in this diagram, okay, here's position 1, here's position n. The alpha problem at I, the forward quantity at IA, is taking all the possible ways of labeling this part from 1 to I, that knowing that they must end with A, and summing all the summing the scores of all the sequences that can label this part, okay, ending with A. So the recursions are pretty much the same, okay, instead that here before we had a max, now we have a sum, and here before we had a sum, and now we have a product, okay? So you can see that we're changing the semi-ring, but the structure of the dynamic programming is the same, okay? And if I want to get So once I have solved I have all the forward quantities for every I and A, then the total sum product is here. Okay, it's at position N. I need to sum over all the A's. Okay, so the cost is exactly the same because the recurrence is exactly the same. And the symmetric algorithm is called the backward one, which proceeds in a backward fashion. Okay, so if the forward was the blue, the blue quantity, which is the sum of this part, then another way to solve the same problem is by defining backward quantities. So the backward quantity, it's a bit more weird because it's kind of the symmetric quantity, but the backward quantity at position I and tag A is in the diagram. If we consider position I and we consider an A here, it is actually the sum of all ways we have to label the rest of the sequence. Okay, knowing that we have an A here. Okay, so the detail of why we define it like this, it's a bit of a technicality. Doesn't really matter. Okay, but while the backward, the forward quantities we proceed left to right, the backward quantities we're going to proceed right to left. Okay, and it's gonna compute the same. It's a different way to divide the problem. Okay, but proceeding differently. So the recursions now are different, using again the sum product instead of the sum product. Okay. So like the Viterbi and the forward algorithms, the backward algorithm also runs in linear time in the length of the sequence and quadratic time in the number of levels. Actually, 3 slides ago, I posed you some homework, which is write the Viterbi algorithm, but proceeding right to left instead of left to right. And here I'm writing the backward algorithm, which actually proceeds right to left, but instead of using the sum, the max sum semi-ring, it uses the sum product semi-ring. Okay, so I'm giving you now the type of equations. If you want to look at the Viterbi algorithm, but proceeding right to left instead of left to right, it's actually a combination of this algorithm, but changing back to using max sum instead of sum product. I'm going to describe now log linear models for sequence prediction. So what are log linear models? So log linear models are models that compute conditional distributions in the context of sequence prediction. Okay, so we're going to now talk about models that have this probabilistic view on the task. Okay, so let's first make sure that we all are on the same page in defining what is a model that computes conditional distributions. Okay, so we're in the context of structured prediction. So let's look at this part. We're in the context of structured prediction. So these are for sequence prediction, these are sequences, input ones, and these are output sequences. Okay, so conditional distribution is one probability distribution over output sequences given a certain input sequence. Okay, so this means that for any sequence that we have, input one, we have a probability distribution over every possible output sequence. Okay, so because this is a structure, this is sequence prediction, these distributions are over an exponential number of values, but in principle that doesn't change the definition of conditional distributions. Okay, but in addition to that, we are defining a model. Okay, what is a model? So one model is parameterized by W. And what this means to have a model for conditional distributions is that given one certain model fixed, this model, for any x that we provide, it computes the distribution over y values. Okay, so the same model will compute one distribution for each possible input sequence. Okay, so this is the definition of a conditional model for sequence prediction. And so log linear models are a specific way to define this. Okay. And as a matter of fact, they can be seen as linear models that, given a certain x and y, they have a feature representation of x and y times a weight vector. Okay, so this gives a score. So the way that the probability is defined is by taking this score of a linear model, exponentiating it, and then dividing it. Okay, so what's the effect of this? So a linear score can be negative or positive. Okay, while if we do an exponentiation, now this value is going to be between 0 and infinite. Okay, it's going to be on the positive side. And what is this normalizer? Well, this normalizer is called the partition function, and it's that given a certain input, it's the sum of all the exponentiated scores over all the values of the distribution. Okay, so while these exponentiated values are in the positive side, the normalizer ensures that these are normalized back to 1. Okay, so it's just a normalizer. Okay, so by having an exponentiation and this normalization, we get that the scores of a linear model are turned into a conditional distribution. Okay, this might actually seem, this is a very common model in statistical modeling, and the way it's defined like this, it's because it has a number of important properties in terms of statistics. And actually, you might be already familiar with that. Logistic models do this sometimes for binary classification. Okay, so this corresponds to a logistic model for in the case where we have many values. Okay, or in the jargon of neural networks, this is no other operation than a softmax. Okay, but applied at this scope of full sequences. Okay, so in case that we have a conditional distribution over y is given x, and we're asked, okay, now I would like to predict the sequence given an input. Okay, so what we'd like to do with probabilistic models is to pick the most likely output sequence according to the model. Okay, so which brings the question: why do we care about defining probabilities? Okay, and here there's different answers. Okay, first of all, we don't need to, in order to make prediction, to model prediction and machine learning, we don't need probabilities, but probabilities are very useful. Okay, because as we will see later, if our model defines probability distributions, then we can use a number of loss functions that are only defined whenever we have probabilistic versions of a model. Okay, that's one reason. Okay, it gives us criteria for training a model, but there's other reasons. Okay, there's a lot of literature on probabilistic inference, where we have components that are distributions, either joint or conditional ones, and by putting them together, we can plug them, and then we can build reasoning systems. Okay, I'm not going to focus that at all, but sometimes you want a distribution, not because that will facilitate estimating the model, but actually because you are required, or whenever you want to integrate your functions, you'd like to have probabilities. And obviously, the reason behind that is that a probability distribution immediately gives us a notion of uncertainty, right? While a non-probabilistic model is unbounded, a probabilistic model is actually bounded, okay? Which is the role of this normalizer. Okay, so why are we calling it a log linear model? Okay, so let's take the expression we just defined, and let's apply the logarithm of that. Okay, so we substitute, we get the logarithm of this expression, but because it's a log of a fraction, we can just take logs of the log of the numerator minus the log of the denominator. Okay, and because it's a log of an x, the log and x cancel, and here we have this term. When taking the logs, we get this term minus the logarithm of the partition function, which I'm substituting here. Okay, so it turns out, so the term here is just a linear in the log space. The term, this term here, is just a linear score of x and y times w, and this term here, all of these, note that it does not depend on the y. Okay, it only depends on the x. Okay, so this log of z is a constant for a fixed x. So if I fix x, I have a constant here. Okay, given by this model. Okay, so the name comes from the fact that in the log space, our computations are linear. Okay, so what we're doing here is we're employing a linear prediction, namely this form of prediction model, in order to model log probabilities. Okay, so in the log space of the probabilities, we have a linear model. Okay, here's the name. Let's be more practical. Let's say that somehow we have a model, a log linear model for sequence prediction. This is already trained, and we want to make predictions. So we're given x, and we want to compute y. Okay, so if we assume that the feature representation factors into bigrams, then we can do as follows. Okay, so we're asking for a given x, we're asking for the sequence that maximizes the probability. Okay, the most likely sequence in this conditional distribution. Okay, I'm going to substitute. Okay, and the first thing I'm going to observe is that this quantity here is constant for x. It does not depend on the y. Okay? It's a constant. Okay, so because I want to pick the sequence that maximizes, a constant is irrelevant. Okay, it will change the value, but it will not change. It will change the value of a score of a sequence, but it will not change the argument that maximizes the score. Okay, so I can drop the normalizer here, and I get this expression. And for a similar reason, I can take the log. Okay, if I'm maximizing a function, the maximizer is going to be the same if I maximize the log of that function instead. Okay, so maximizing a function or maximizing the log doesn't change the argument, the maximizer. Okay, so I'm taking the log, and then I have an expression which is exactly the same of what we were seeing before. Okay, so because the score of a certain sequence is a sum over bigram scores, I can use the Viterbi algorithm. Okay, so here, once again, I'd like to highlight that in the first part, I have introduced factor models, and factor models have a number of properties, such that the ability to make predictions. Okay, and now in this section, I'm taking a factor model and I'm equipping this model with this probabilistic apparatus, with a log linear model. But a log linear model that is factor is still a factor model. Okay, so all the properties of factor models hold here. So when we work with probabilistic models, there's other computations that we'd like also be able to solve, and these computations are maybe specific to these probabilistic models. Okay, so one is the probability of an output sequence given a certain input. Okay, so before the problem was to obtain the argmax. Okay, so here, because I wanted the argmax, I could get rid of the probabilistic apparatus. Okay, but sometimes I want to actually compute the distribution. Okay, maybe for a certain, maybe I have for a certain x, I have 3 or 4 y sequences that I'm giving, and I want to actually assign probabilities to that, to have a notion of certainty. Okay, so in that case, I need to compute this expression. Okay, and if the x and y is given, the denominator is easy. I just do the inner product and do the exponentiation. Okay, but what's going to be difficult is this z. Okay, to compute z, we need to sum over an exponential number of sequences. Okay, because this is how it's defined at the very beginning. I defined the normalizer for a certain input given a model is the sum over all possible sequences that apply to this input of the exponentiated score for this sequence. Okay. So, but what I can do is as follows. So I can assume that this feature vector over sequences is a factored one. Okay, so what I can do is substitute and put the weight inside. So I can translate this, instead of seeing it as a product of a feature vector representing x and y, I can see this score as a sum of scores over bigrams. Okay, so I'm turning this into a sum of scores. Okay, and then because I have the exponentiation of a sum, I can turn this into a product of exponentiation. Okay, and so note that here what I'm having is a sum product computation of the scores of the model that assigns to trigrams in an exponentiated. Okay, so because this z can be expressed as a sum product computation, I can apply the forward algorithm using exponentiated scores of my model. Okay, so once again, because of the results that we saw in the previous section about dynamic programmings, in case that we have factored scorings, now I can make use of those algorithms in the context of this model. Okay. So another computation that is very useful is that of marginal probabilities of just a single label. Okay, this again is a computation that is well defined whenever we have probability distributions, and in this case, our model is computing distributions over full output sequences. Okay, so what we're asking here is, what if we only want the distribution or the probability of a single label? Okay, we don't care about the labels here. What we want is, what would be, given this sentence, what would be the probability of having a person here? Okay, so what we are asking is to compute the marginal distribution. Okay, we have a distribution over full sequences, and what we'd like is the marginal distribution of just a single label, a single position in there. Okay, so how do we define it? So I'm calling this the marginal distribution of ui, namely the probability, right? I'm calling this mu I of a. Okay, that would be the probability that at position a I observe this output symbol a. Okay, so this is defined. Okay, so this is the definition. Okay, given this sentence, what is the probability that at position I have an A? Okay, so this is defined using the theory of the definitions of marginal distribution as since my distribution operates at the sequence level, my model defines distributions at the sequence level. So I'm going to consider all possible sequences that do meet this condition, okay, that the position I is A. And I'm going to sum the probability of each of such sequences, okay? So this gives me a well-defined notion of the distribution at this position. So there is some algebra that one needs to apply, but the idea is that after some algebraic massaging, okay, if we manipulate the expression and apply the fact that underlying this distribution there's a factored representation, we can write down this quantity as a probability of three terms, okay? It's the forward quantity at position I and label A times the backward quantity at position I and label A divided by the normalizer of the distribution, okay? So this, I introduced these alpha and beta terms, forward and backward terms, when I was discussing generalizations of Viterbi. Essentially, the alpha term will consider the probability of all subsequences that go from the beginning to this position and that have this label, okay? While the beta will consider the probability of all the sequences that from this point on complete this part, okay? Such that if I do the product of alpha and beta at a certain position with a certain label, I get the sum, the unnormalized sum of all the sequences that have this tag at this position, okay? And if further I apply the normalizer, I do get the marginal distribution, okay? So this again requires perhaps going through this derivation to fully understand it, but the statement is as follows, okay? Whenever we have a factored model at global level, we can compute marginal distributions at local level for a single label efficiently, okay? Because both the three quantities can be computed by means of forward backward. And there's a slight extension of these marginal computations, which instead of asking for the probability of one label at a certain position, we're asking for the probability of a bigram of labels at a certain position, okay? So given the statement is, given this sentence and fixing this position, what is the likelihood under the model that these two words are labeled like that, okay? I don't care about the others. As a matter of fact, I would like to consider all combinations that do have this bigram in here, okay? So once again, it's now a definition of marginal that instead of considering one label, it considers two adjacent labels at a certain position, and it's going to consider all possible sequences that do have this labeling in here, okay, this substructure in here. And so summing for the probability that our model gives to these sequences will give us a well-defined notion of marginal. So once again, there's some algebra in here, but we get that to compute this quantity, okay, what we need is the product of the forward quantity up to position I-1 with this tag times the backward quantity up to position I times the exponentiated score that our model assigns to this bigram at this position, okay? So this is perhaps a bit hard to digest here if you've never seen that, but again, the useful property here is that these quantities that are useful in many different ways, okay, can be computed efficiently only because we're assuming that the scoring and representation of our input-output sequences follows a factorization, okay? So here I'm closing this section on presenting factored sequence prediction models. We also saw before greedy models for sequence prediction. So in factored representations, the main essential idea is to take output structures, output sequence, and consider parts of this, okay? For example, consider bigrams of the output, okay? And then have a representation that is factored at this level, okay? So once we have these representations, we can compute these feature vectors at the global level and simply define a linear model for structure prediction, okay? Knowing that this is the feature representation is factorized, will typically allow to solve this Argmax problem in an efficient way, okay? So I presented the Viterbi algorithm to do that, okay? And I also presented if we equip our linear model with a probabilistic log linear apparatus, so we can also compute marginals using forward backward, okay? So this is all I have to say in terms of families of models. And next, I'm going to focus on finally methods for learning the parameters of models, okay? So namely learning this W, okay? And I'm going to present the structured perceptron as a very simple method for this family of models, and also methods precisely based on log linear models, okay? And I'm going to present loss functions based on two variations of this.
Yeah, that was the end of the second part. I think it's good to do a break here.
Yeah, I think it's a good idea. So let's do 10 minutes break, okay?
Okay.
Okay. Thank you. See you later.
now that we know the form of structured prediction functions and their computational properties, we're finally going to present learning algorithms, namely algorithms to estimate the parameters of the models. I'm going to cover three algorithms. One is the perceptron algorithm for structured cases, and the other two algorithms are in the context of probabilistic log linear models. So perceptron is possibly the most simple learning algorithm that is possible. So you covered perceptron in the first lecture on learning classifiers, okay? And essentially the algorithm has the same form. So it starts by initializing the weights to 0, and then for a number of iterations, it visits all the training examples, X and Y. X is the input, Y is the correct output, and computes the best solution, Z, for the example, okay, under the current weights, okay? So then we have the correct solution and the best prediction made by the model, okay? So perceptron is a mistake-driven algorithm, meaning that it doesn't update to the parameters whenever there is a mistake, okay? So this is what the step 2 is doing, okay? If the predicted solution is different from the structured one, then we're going to do an update, okay? And the way we do an update is again analogous to how we do it for the binary or multi-class case. We're going to take the current vector of parameters, we're going to add the feature vector relative to the correct solution, and we're going to subtract the feature vector relative to the predicted solution. So we do this for a series of iterations for all the training data, okay? This is called epochs sometimes. And so once we've run this, we return W. So this form of structured perceptron, as I said, is essentially the same as the perceptron for multi-class, okay? The one that introduced this variant for the structured case was Mike Collins, okay? So this perceptron is sometimes called the Collins perceptron. And essentially the main idea behind this is that if we can frame a structured prediction as a linear prediction, which we did in the last section, okay, then this computation is well defined. We can recover the maximum scored solution and the current parameters for a certain input, and then the update rule of perceptron will work as expected, okay? So essentially it's just connecting the required properties of perceptron to a new scenario where we do actually have the ability to compute the argmax, okay? Obviously this will be possible if F is using some factorized form, okay? Because we can employ Viterbi in case of sequence prediction or other algorithms in case of other forms of structured prediction. So there is a modification to the perceptron, which is orthogonal to the fact whether we're predicting binary, multi-class, or structures, which is perceptron with averaging. This was introduced by Freund and Shapiro, okay, in the late 90s. And so it's again very simple. So instead of having one weight vector, we're going to maintain two, okay, the same one as before, but also an average version of the weight vector, okay. So the algorithm proceeds the same as before, except that there's a third step that will update the weight vector irrespective of whether there was a mistake or not, okay. So, and then we're going to return this average vector, okay. The main mechanics of the algorithm is using the regular weight vector, but at the end we're going to return the average one. So the idea behind this averaging technique is the one behind classifier combination, okay, which tends to improve a combination of classifiers, tends to improve one classifier alone. So here we know that after every update, there's a new classifier, which is related to the previous one, but yeah, it's a new one, okay? So this averaging is essentially combining all the classifiers that have been generating during the perceptron run, okay? The interesting property about this, that is shown here, is that one can relate this average version of perceptron to maximization of margin, okay? The average version will favor to have a W that has large margin on the training set, okay? And as we know from the theory behind supervector machines, large margin is related to improve the generalization error on unseen examples. to understand the mechanics of perceptron, let's look a bit closer to this update rule. Okay, and to do so, let's look at one example. Okay, say that the input is this sentence, the correct output is this one, but the sequence predicted by our model is this one. Okay, it's a different one because it differs by one label. Okay, so what is the update rule? Okay, the update rule says that the update we're going to do to W is the feature vector corresponding to the correct sequence Y minus the feature vector corresponding to the predicted sequence Z. Okay, Z must have some mistake in here. Okay, because we're going to work with factored models, the form of these two feature functions is actually a sum over features at the bigram level. Okay, now say that there's a single mistake. Okay, there's a single mistake here. So the observation I want to do is that in case that there's only a few mistakes, say one, okay, only a few feature vectors at the bigram level will be affected. Okay, so in particular, if the mistake is here, this affects two positions at the bigram level, namely this one, person, person, we're changing to person location, and then we're also changing this position here, location dash, sorry, person dash to location dash. Okay, but the feature vectors around this area will cancel, okay, because we are summing and then subtracting. Okay, so the feature vectors in here will do the same. So in practice, what's going to happen is that the perceptron updates are sparse. So why is it sparse? Maybe at the beginning, perceptron will do lots of mistakes, but there will be a point that perceptron, the classifier will be already pretty good. Okay, and maybe it will do a mistake from time to time. Okay? But the mistakes will look like this. Okay, in a given input, which might be a very large sequence, maybe there will be 1 or 2 or 3 mistakes out of maybe 50 elements. Okay, so meaning that the update to the weight vector can be expressed only as these additions and subtractions related to the labels that are mistaken. Okay, all the features related to the labels that are correct will not be updated. Okay, so this results in an update, a sparse update of feature vectors, and in case that the features vectors themselves are also sparse, which is the case for indicator features, then the whole update will be sparse. Okay, so if perceptron constructs W by a sum of updates across all the iterations, then summing a number of sparse updates will result in general in also a sparse weight vector. Okay, so perceptron has this property, which in some cases can be very useful, that even though our feature vectors might be extremely high dimensional, if each of the feature vectors is sparse, typically the resulting weight vector will also be sparse. So some properties of the perceptron, just to state them, okay, it is an online algorithm doing one update at a time when it finds an error, okay. So often this is very efficient, okay, and is a lot quicker than, let's say, a batch algorithm. A batch algorithm looks at all the training data, computes an update, and then goes to the next iteration, okay. So this is similar to stochastic gradient descent in the sense that it's a gradient descent algorithm that stochastically just picks a few examples in order to do the update. So perceptron actually has this flavor. Okay, so some properties in terms of training error say that the training data is separable. Okay, then perceptron will converge to weight vector that has no training error. Okay, and separability here, even if we are at the structured level, separability means the same thing. It means that there is a W. So if a Y is the correct structure and Z is any of the incorrect structures, even if there's exponentially many, separability means that there is a W by which for any X in the data, okay, we obtain separability between Y and any of the Zs. Okay, so the same convergence properties also apply here to the structure case, but not also in terms of training error. In terms of generalization, a perceptron also has properties, especially we use the average version. Okay, so in terms of averaging, it is very useful in NLP tasks. It improves the performance a lot, okay? In the sense that while the regular perceptron is a moderate algorithm, using averaging typically improves a lot, and it's on par with other methods for linear structure prediction, okay? So perceptron overall is very quick at reaching a good solution, okay? This is very useful when developing models, because typically when developing models, we're trying different sets of parameters, different decisions of the model, okay? So it's very good to have a training algorithm that after running for just a while, okay, we already have a sense of how the performance of the model will be, okay? Then typically, if something in the model is not looking good, we quickly see that the performance will not be good, okay? So we can discard that type of model. So, and as I said, typically performs nearly as well as conditional random fields, which is an algorithm that we will see next, and you'll see it's a lot more involved in terms of the justification, the algorithms, and the computations behind. Okay? So in principle, perceptron requires to pick the argmax solution at every step. Okay, if our representation is factored, if we are using a factored model, this can be done using the Viterbi algorithm. Okay, so for the structured case with factored models, we can just run perceptron the normal way. But as I discussed, there's a number of an important family of models where transition systems where it's not possible to recover the argmax solution, but only an approximation. Okay, so there's been a lot of research on using structured perceptron using beam search. Okay, so beam search is just an approximation to the argmax. Okay, we cannot guarantee that beam search will find the argmax, but it will find a good solution that is probably very close. Okay, so there's a lot of work. I'm mentioning here 3 papers in the context of structured perceptron for different types of transition systems. Okay, and with different observations. So I have some numbers here. So the first is some experiments that I ran about 10 years ago on a parsing task. Okay, with a factor model using perceptron. Okay, so this is the number of times, the iteration is the number of times I visit the full training data. Okay, so we can see here that so while the performance seems to be stable around here, around just below 92, only after the first iteration we're already at 90.8. Okay, and this quickly improves. So only after one pass over the training data, we are very close to the final performance. Okay, so as I said, very quickly, perceptron gives us an indication of how good the model will be. Okay, here's also graphs by Zhang and Clark using perceptron in conjunction with beam search with the transition model. Okay, so these 4 different sizes of the beam. Okay, so using beam 1 is just using greedy prediction, obtains this performance, and we clearly see that if we make the beam larger, okay, meaning that the predicted solution will be less of an approximation, okay, the performance really improves. Okay. So next, I'm going to present learning algorithms for structured prediction in the context of log linear models. So to recap, a log linear model is actually a linear model that defines the conditional distribution of output sequences given an input one. Okay, and it does so by exponentiating the score given by the linear model and then dividing by this partition function that is just a normalizer. Namely, it's the sum of exponentiated scores for all the sequences. Okay, so we already saw in the previous section that if this feature representation factors, let's say at bigrams, then we can recover the most likely output sequence given an input one using the Viterbi algorithm. Now we're going to look at the learning problem, which is given training data, collection of examples, how do we estimate the parameters of the model? And there's a strong motivation to use probabilistic models as opposed to just non-probabilistic ones, because a probabilistic model defines the conditional log likelihood of the data. Okay, this quantity, especially in the literature of deep learning, is also called cross entropy. So what is the conditional log likelihood of the data given a model? It's a quantity that measures how well our model is explaining the data. Okay, more specifically, since ours is a probabilistic model, for any example, we can compute the probability of the correct output for the example. Okay, so this is our data. Instead of just taking probabilities, we take the log probability in such a way that if we sum over all the examples, this is a measure of how well a W is explaining the data. Okay, so a good set of parameters, a good W, will give a high value for the probabilities. Okay, while a bad setting of the parameters will give low values. What we want, obviously, is that under our model, the correct examples have as much probability as possible. In the limit, we would like that the correct output for each input has probability 1, even though this is not attainable under this kind of model. Okay. In any case, this likelihood gives us a criteria in order to choose one set of parameters. Okay, and so specifically, given that we have this notion, we would like to pick the W that maximizes this log likelihood. We're going to put this criteria in the context of loss minimization with regularization. Okay, so this is a standard way in which we write the objective functions behind a learning algorithm. Okay, so out of all the space of parameter vectors of the dimensions, we'd like to pick the parameter vector that minimizes a combination of a loss and regularization. Okay, the loss is a measure of actually how bad the parameters explain our training data, while regularization is a notion of complexity. We'd like to pick the parameter vector that minimizes the balance between explaining the data and having low complexity. Okay, so if we want to use the measure I just introduced before, the entropy gives high values for good settings of the parameters. So here's why: because we're minimizing and not maximizing in this form, we're just using the negative log likelihood. Okay, this negative is just because instead of a max, we're using a min. Okay, so we're minimizing the negative log likelihood, which is equivalent to maximizing the likelihood. And we're adding a regularization penalty, which for linear models, it's standard to use an L2 regularization. Okay, as is typical in this type of objectives, there's a parameter lambda that controls the balance between loss and regularization. So this objective here is convex because both the loss is convex with respect to the parameters and the regularizer too. So in that case, we're dealing with a convex optimization problem, and one key method to solve that is just use gradient descent in any of its variants. For example, BFGS or stochastic gradient descent is also very popular for any type of such problems. What we need to make sure in the context of a structured prediction, where these losses are defined over exponentially many outputs for each input, we need to make sure that the computation of the gradient is tractable. Okay, so I'm going to present two common losses for log linear models that make learning tractable. Okay, there's two choices, and I'd like to present these two choices. One is what I will call the local loss, where we're going to assume that the probability distribution over sequences that I define it further decomposes into smaller conditional distributions. Okay, and the other approach, which I'm calling global loss, which is also sometimes called conditional random field, I'm not gonna take this assumption, but I'm going to use a weaker assumption that just assumes that the feature representation of XY pair decomposes into factors. Okay, which is actually what we've been assuming in most of the lecture when it comes to factor models. So let me get in detail about these two approaches. Let's start with the first one. So the first variant is the local log linear loss, which appeared in a paper by McCallum, Freytag, and Pereira in the year 2000. The paper was called max entropy Markov models, and many people still call these methods like that. Okay, so the idea here is that we want to model these conditional distributions of full output sequences given full input ones, but what we're going to do is to decompose these distributions using the chain rule. Okay, so we're going to say that the probability of a full output sequence is the probability of the first symbol times the probability of the rest of the symbols given the first. Okay, always in the context of a certain input. Okay, and so we can further apply the chain rule to this subsequence here. So if we work it out, we'll say that this distribution over sequences can be decomposed as a product of distributions, which are of the first symbol, and then for a product, the distributions are over the next symbol given all the previous symbols generated. Okay, so essentially what I'm doing here by means of the chain rule is to turn a distribution over sequences into distributions that are over one symbol alone. Okay, over the first symbol or over the next symbol given all the previous part. Okay, so I greatly simplified this part of the distribution, but I'm actually making the conditioning part a bit more complex by adding now not one sequence but two. Okay, so here where the Markov assumption comes. So this is a typical Markov assumption that says that when it comes to modeling the probability of the next symbol given all the previous symbols of the output sequence, most of the assumption says that only the last symbol here is relevant. Okay, so the probability of this given the full sequence is actually the same as the probability of a symbol given only the previous one. Okay, so this is an independence assumption that essentially says that the previous symbols to y minus I minus 1 are just irrelevant in order to model this probability. Okay, this is obviously an assumption that in most cases we can observe that it's not true. Okay, in NLP, this Markov horizon principle doesn't apply, but still we can take the assumption and move on. Okay, so by first decomposing into conditional distributions per symbol, and then applying the Markov assumption, I can now write that the distribution of output sequences given input ones are just products of these conditional distributions, okay, which are of one symbol at a time, conditioned by the full input sequence and just one symbol. Okay, so I'm going to call this the global conditional distribution, which is over sequences, and I'm going to call this the local conditional distribution over just the next symbol given the previous one. So the one consequence of using this Markov assumption is that in this distribution over just the next symbol, the normalizer is also local. Okay, so this is a lot more simple than before. Before we had to normalize, before the distribution was over full sequences, and we had to normalize over the full space of sequences. Now, in the context of a sequence, an input sequence, a certain position, and the symbol in there, we just need to predict what's the symbol coming next. Okay, so it's a distribution over just a set of labels, and so the normalizer is only over the set of what are the next labels. Okay, and it turns out that if we we do the math and apply these assumptions to the definition of log likelihood that I gave, we can see that actually the log likelihood is also local, meaning that the likelihood of the data given the model weights is a sum of terms where we're only looking at how good. So the sum will be over each example from 1 to m, and in a given example, I'm going to loop over the positions of the sequence, okay, from 1 to n. So n would be the length of the kth sequence. And so for each of these positions in a training sequence, I'm going to be asking, according to my model, what is the probability of the next symbol, the correct one, given the input, the kth input example, and the current, and the symbol, the correct symbol previous to that position. Okay, so the likelihood is now a sum over factors of the training examples. Okay. And this fact, the fact that the likelihood now looks at factors, is really analogous to multi-class predictions, okay? Because given a certain position and a symbol, we're asking what's the likelihood of the next symbol, okay? So it's like a multi-class prediction over the next symbol, okay? So this is what really looks the same as maximum entropy models for multi-class prediction. And so if we look at the gradient of this likelihood function, okay, we can see that the gradient loops over examples and positions, and it's simply taking the gradient is taking the difference between the observed feature values at example k, position I, and relative to the correct labels at that position, minus the expected feature values on that position based on the distribution we're trying to estimate. Okay, so once again, the type of updates are relative to the prediction of just one symbol at a time, given the prediction of one symbol at a time, given the correct previous symbol. Okay, so this is the local approach that essentially reduces to multi-class maxent in the context of sequences. And the alternative to that is to use a global approach. And so this was presented by Lafferty, McCallum, and Pereira in year 2001. I should note that this is just a year later of the previous paper, and two authors are the same of the two papers, namely McCallum and Pereira. So they were really after this kind of probabilistic approaches to sequence modeling. So they came with this important paper called Conditional Random Fields for learning sequence models. So the idea at this point actually might seem quite natural. Okay, we consider once again the distribution of full output sequences given an input 1, as I defined, and the likelihood, which is what I defined, we're going to keep it at the global sequence level. Okay, instead of applying additional Markov assumptions and trying to break down this distribution at the global level into smaller distributions that are at the symbol level, at the local level, we're going to keep it like that. Okay. So in order to optimize this log likelihood at the global level, what we'll need to do is, in the context of gradient descent, we need to take gradients of this with respect to the parameters. And so all we need to do is to make sure that we can compute this gradient. Okay. So and here is the gradient. It takes some work to derive it, but here it is. Okay, it's the gradient of this global conditional log likelihood with respect to one parameter at a time. Okay, so it's the sum over training examples, where for each training example we consider a difference between two feature values, or we could also express it in vector form. Okay, so it would be the difference between the feature vector corresponding to the correct solution and the expected feature vector with respect to our distribution. Okay, so the expected feature vector will consider every possible output sequence, consider the feature vector, and weight it by the probability that our model assigns to it. Okay. So first, one note, actually a couple of notes. The first is that this expression works at the global level. Okay, it's feature vectors of complete input-output sequences, both the observed one and expected one. Okay, so this is all operating at the global level. To make things tractable, we're going to have to assume that we have a factorization. In this case, I've written over bigrams. Okay, this is as we saw at the first section. Okay, in the context of factor models and factor models at the scope of bigrams. Okay, now if we do assume this is going to be tractable. Okay, and where is the main problem with respect to tractability? The main problem is that this expected feature vector, okay, is using our conditional distribution over sequences. Okay, so it's a sum over all possible sequences. Now, obviously, we cannot do this in an exhaustive way. Okay, so in order to make for this to be possible, for this gradient to be computable in tractable time, we'll need to be able to compute this expected feature vector quickly. Okay, and so it is by assuming this that we can arrive at an expression that looks a bit long, but I'm telling you it's an expression we can compute efficiently. Okay, and the main idea is that so this is for all the examples. Okay, we're going to look at just at the single example and just at this term here. Okay, so I'm having that this is the expected feature vector of a certain input. Okay, which is I'm going to consider all possible output sequences, consider the probability under my model for this candidate sequence, and then given that they have an X and a certain Y, I'm going to consider the feature vector for this. Okay, so these feature vectors are averaged by my distribution. It's an expectation. Okay, so instead of having to loop over sequences, I can turn this expression into something that looks like this. Okay, so this sum here that sums over positions of the sequence goes at the beginning. So I'm summing over positions, and then I'm summing over all possible bigrams that apply to this position. Okay, and then because my feature function applies at the bigram level, so this gives me values for this. Okay, I'm looping over positions and every possible value. So I'm considering the feature vectors at each position with every possible bigram. Okay, and I'm weighting each of these feature vectors by the marginal probability. Okay, so what is the marginal probability of a certain bigram and a certain position? Okay, this marginal is the probability that under my model, I observe this certain bigram at given an input sequence. Okay, it's the probability of having this assignment of bigram AB at position I in this sequence given by computed by my model. Okay, so actually, this you might recall at the end of the first part of the lecture, when I was describing computations we can do with factorial models, I introduced this quantity. Okay, the marginal probability of observing a bigram in a certain position. Okay, so these quantities can be computed with a variant of Viterbi algorithm called the forward-backward. Okay, can be computed in linear time with a quadratic term that is the number of labels. Okay, the number of this quadratic term is the number of bigrams in our system. Okay, so putting things together, if we run forward-backward, we can compute these marginals for each possible position and output bigram. And so with these marginals, we can compute this expectation required to compute the gradient. Okay, so by plugging everything together, we have an expression. We have an expression of the gradient of the global likelihood that we can compute. And so we can use gradient descent in order to train a log linear model at the global level. So in summary, CRFs, or conditional random fields, are log linear models for sequence prediction that model the global distribution of full output sequences given full input sequences. So to make computations behind this model tractable, we need to assume that the representations factorize on label bigrams, and by assuming that, all the computations can be done efficiently. Okay, so the form of the model when it comes to predicting what is the best output sequence given an input one, the probabilistic part of the model is not necessary. We're just looking for a maximization problem, so we can get rid of the probabilities and just use the CRF as a linear model, and we can solve this using Viterbi. Okay, again, making use of the property that computations factorize at label bigrams. Okay, and when it comes to parameter estimation, if we have this log linear model, we have a notion of likelihood of the data, or maybe conditional likelihood of the data, and so we can employ routines based on gradient descent in order to obtain the W that better explains the training data. Okay, given our representations. Okay, so we saw that if we want to train this model from the global level, okay, we need the computation of the gradient requires forward-backward. Okay, so in the context of CRFs, we see that factorization and the computations behind that are necessary for two things. Okay, so to predict we need Viterbi, and to train the model we need forward-backward. Okay. The next question is, should we use a local or a global loss? So let's recap and see what are the differences. Okay, what I like to highlight is that the two approaches, they both use the same factorization. Okay, when we take the local loss approach, we're taking the global distribution and decomposing it as a product of distributions. Okay, and each distribution at each position is expressed like that. Okay, so we can see that the feature function is at the bigram level. When we take a CRF, we don't decompose this distribution, but in order for the model to be tractable, we must also assume that the feature representation factorizes. Okay, so we could write the expression like that. Okay, so you can see that the two feature representations have exactly the same signature, okay? So they use the same factorization, the same feature signature, so that means that they represent input-output sequences in exactly the same way. When it comes to making predictions, and they use the same decision function, okay? So what is the difference, okay? It's not in the expressivity, it's not when it comes to making predictions, they use the same routine. So the difference is actually in the normalization, okay? And the difference is in the loss function. By employing by making local or global assumptions about the probabilistic distribution is actually affect the loss, okay? And one quantity that is different in these expressions is actually the normalization, okay? In a global distribution, the normalizer is over all possible output sequences that can be assigned here. Okay, so the normalizer is global. While here, the normalizer is local, okay? Namely, at each position, we want the distribution over the next symbol. And then we move to the next symbol, and then we are asking for the distribution over the next symbol, okay? We're requiring that at any point, the predictions over the next symbol are a distribution and sum to one, okay? So when it comes to optimizing the parameters, when it comes to optimizing the likelihood, in the local case, at each position, we're going to require that the distribution over the next symbol puts all the weight on the correct symbol. While in the global approach, we're not necessarily requiring that. We're requiring simply that given the input sequence, the correct sequence has the maximum likelihood, okay? Is the one that has maximum probability, okay? As a matter of fact, one can see that these normalizers are a special case of this, okay? So if I take the product of all the normalizers at all the positions, I do get a normalizer like that, okay? So I could write the global distribution as a product of scores times a global normalizer that is a product of normalizers, okay? So this fact highlights a difference, namely that when we are doing local loss optimization, we are imposing that the global normalizer is actually computed as a product of normalizers, okay? While in the CRFs, we're not doing that. We're just more relaxed, okay? So all the models that are local models are also global models. But global models include parameter settings that are not local models, okay? If you want to read more about this difference, you can take the original paper of CRFs, okay? They introduced this problem, the label bias problem, okay, which is what might go wrong if you take this assumption, okay, that the global normalizer, you require that is a product of normalizers at each position, okay? So this was commented here, and actually this was one of the main motivations to come up with the CRFs. And years later, 4 years ago, this is a very nice paper by Andor and others, where they revisit this in the context of actually neural approaches to sequence prediction. They compare a sequence model, a neural one, that is trained either, the same model is either trained using a local loss or a CRF style of loss, a global one, okay? And they show that in some cases, the local loss can really suffer, okay? Because it's imposing a condition that is too strict on the data, okay? We only need that the global sequence is the correct one. We don't need that each local step is perfect when training, okay? While by using this relaxed form of global learning, the performance can improve significantly in some cases. So I recommend that once you are familiar with structured prediction in general, you revisit these papers and take a closer look at this phenomenon, okay? In practice, however, maybe I should have started here, there is an advantage of doing the local loss, which is that when I'm doing local loss, I'm essentially reducing sequence learning to multi-class learning, okay? Where we have a multi-class problem for each position where we're trying to predict what comes next, okay? It is a very simple way to learn a sequence model, okay? While in contrast, if we want to train CRFs, we need to repeatedly run forward-backward in order to compute marginals, okay? So the computation of marginals is essential in order to be able to optimize this global loss. On the other hand, when it comes to moving away from sequence prediction and applying this framework to other problems, like maybe parsing, okay, it's going to be easier to just apply CRFs. Why? Because in essence, what we're doing here is to put more inductive bias to the algorithm. Okay, we're telling the algorithm where we're actually telling where there could be local normalizations. Okay, and by putting this bias, we help the training process, and it becomes computationally easier. Okay, but it's not obvious in other problems where are the scopes where the distribution could normalize locally. Okay, so while in sequences it is natural to think of these local normalization steps, it is not for other types of structures. So when it comes to extending to other forms of structure prediction, it might be easier to just think about general CRFs. And this is essentially all that I have to say about learning. Okay, so to recap, the summary so far is that I've essentially introduced this family of models, okay, for sequence prediction, namely factored models that have this representation factored at the bigram level, okay? And by assuming that our computations factorize, the main advantages here is that we can do tractable computations, okay, for decoding, for solving this argmax problem, we use Viterbi. And when it comes to estimating the parameters, for example, with CRFs, we can use formal factors. So when it comes to parameter estimation, namely estimating the W given training data, I have presented perceptron. I have presented methods based on optimizing the log likelihood. There's also variants of SVM for structured scenarios. I haven't covered that, but they exist, okay? And essentially what I like about this paradigm is that, so these methods exist for binary classification and multi-class. And so in the structure case, we can see these algorithms as natural extensions from the binary and multi-class classification, okay? Where we're essentially, it's essentially a structure prediction is like a multi-class problem where we're choosing one output value out of a number of possible values, just with the particularity that these values are structures and there's exponentially many, okay? So the challenge is not in how we pose learning as a search for parameters. The challenge maybe is how we define a representation that is expressive and that allows to solve for the computations that are required behind these type of models, okay? So once we have established a loss function and we have established the computations, actually optimizing, actually learning the parameters is essentially left to the optimizer, okay? So machine learning, it's been many years that in machine learning, we use general purpose optimization methods, okay? Some of them work better than others, especially because our types of problems have particular characteristics, like for example, high dimensionality or lots of data, okay? So stochastic gradient descent is very popular also in the context of deep learning. In the past decade, there was many research work trying to tailor the optimizer to the actual structure prediction problems. Here, I'm giving you here some references. So these are tailored methods for optimizations. And that's all I have to say with respect to learning methods for structure prediction.
I want to present now a quick overview of dependency parsing, which is a different form of structure prediction problem. Okay, so here the input is a sentence, a sequence, and the output is a tree. Okay, and in dependency parsing, the trees are made of dependencies. So what is a syntactic dependency? Is a relation between two words that encodes the syntactic function of one word with respect to another, and altogether they build a tree. Okay, and why is this useful? It's useful because among many ambiguities in natural language, many of them are syntactic ambiguities. And so the dependency tree is giving us the disambiguation in terms of the syntactic ones. Okay, so for example, this sentence, which is ambiguous, there's a prepositional group here with statistics. And so the dependency from solved to this group is telling that the problem was solved using some statistical method. Okay, while the alternative reading is given by this dependency tree, where the group with the statistics is modifying the problem. Okay, so here we had a problem that had to do with the statistics, and we're solving it using some method. Okay, so dependency parsing is useful in this form. In the literature, there's two types of trees used to represent syntax. One are dependency trees that focus on these relations between words. The other, very common one, are constituent trees,
where the main element are these constituents, okay, which are nested trees. Okay, this sentence, noun phrase, verb phrase. So they are abstract linguistic units that we believe that this this group of words function together. Okay, and the resulting style of tree is a nested tree. Okay, so irrespective of which theory or representation we choose to represent syntax, we'd like to apply a structure prediction in order to do to predict the syntactic tree. Okay, so I'm going to just focus on a couple of approaches to dependency trees, just to highlight that what we showed for sequence prediction is also applicable to the parser task. Okay, so one important family of models are the factor models for structure prediction. So McDonald and others back in 2005, they proposed the first model, our factor model, trained with perceptron or with other variations of structure prediction algorithms. Okay, so here we have that trees are made of dependencies, so the model factors the tree according to its dependencies. Okay, so dependency can be represented as two words, okay, as two index words. So the model is scoring one full tree Y as the set of dependencies it contains. Okay, so each tuple HM is one dependency. These are the indices of each dependency in the tree. And so our model is scoring each dependency HM in the context of the sentence. Okay, so then the model is taking the score of each dependency and making a sum. Okay, and what we'd like is to predict the tree that maximizes the score of the factors. Okay, the score of the dependencies. So I'm not going to go into details. You can check the paper and subsequent papers based on this technique. But the point is that just using this very simple factorization, many expressive features can be encoded here. Okay, so this will result in a very expressive model that performs very well. And the main advantage of this kind of factorization is that there exists tractable algorithms, namely that we can recover the top scoring tree very efficiently. Okay, as a matter of fact, there's two types of algorithms for this kind of factor models. One is framing this problem as a maximum spanning tree. So the idea is that we construct a graph where each node is a word, and then with every two words we have a candidate dependency which is scored by our model. Okay, our model emits the scores for dependencies in the context of a sentence. So each edge represents a dependency between two words, and this is the score given by our model. Okay, so then we just use a max spanning tree routine to pick the spanning tree, the maximum spanning tree, namely the spanning tree that maximizes the score of its edges. Okay, and using the Chulu-Edmonds, this can be done in quadratic time. Okay, so this works as a parsing routine. So there is an alternative parsing algorithm for dependency trees based on the CKY algorithm for context-free grammars. So Jason Eisner, back in '96, came with an adaptation of the CKY algorithm for dependency parsing, and I'm not going to go into any of the details here, but this algorithm runs in cubic time. And one main advantage of this algorithm is that it's very easy to extend to factorization that has larger scope of factors. Okay, so the basic model just scores one dependency at a time, so it scores all the subtrees that look like this in a dependency tree, but we could consider larger factors like one head and two siblings, or even one head with three siblings, or grandparent relations, etc., etc. So what we're doing here is to extend the scope of factors. Namely, we're able to now have features that have a richer encoding because we are giving richer subtrees. Okay, and then this algorithm will be able to recover the tree that scores more, where the score of a tree is the score of each of the subtrees of this kind that it contains. So very expressive and models that have quick algorithms. The second style of structure prediction approaches to dependency parsing fall into the family of transition-based systems. And here there's a very popular transition system for parsing, which is the ARC standard system by Joachim Nubre. So the transition system is described by states and decisions, and incrementally built the parse tree. So in this case, the state consists of two structures, namely a buffer that has the sentence that needs to be parsed, okay, or the part of the sentence that we still haven't parsed. And then we have the stack, which is a list of trees that we have already built, okay? And so given a certain configuration of the buffer and the stack, the parser will pick one action that either is a shift action that takes a word of the buffer and puts it onto the stack as a subtree that has just one word, or left and right arc operations that take two subtrees in the stack and produce a larger subtree, okay? So this process is run until the buffer is empty and we have a single tree in the stack, which is the final tree, okay? So the main advantage is this is that the parsing is very fast. It can be shown to be linear in the number of words, so it's very fast. But it is prone, like all the greedy and transition-based systems, it is prone to greedy mistakes. It is also a very expressive model, okay? It has access to, so at any point, the model has access to the full sentence and the full history of actions in order to decide the best action, okay? And so several works that do actual representations of this have shown that you can really go very far from that, especially now using neural networks to encode this. So I have an illustration by Miguel Ballesteros of how this system works. Okay, at the beginning, we want to parse this sentence and produce this tree. So at the beginning, we have the buffer contains the sentence, and we have an empty stack. And at the beginning, we choose shift operations that take words in the buffer and put them onto the stack. And then maybe we take a left arc operation that puts the dependencies in between these two words and creates one subtree rooted that way. Okay, so it creates this dependency, this action. Okay, and this keeps going until we have an empty buffer. There's still two subtrees, so now we have just one subtree. Okay, so I'm not giving any detail about this construction process, but the point is that incrementally, at any point, the system is deciding one action that will build the tree incrementally. Okay, so at any point, our model needs to choose what's the best action, and in order to do that, it can to choose a left arc here, it can encode all these structures here. Okay, so while this is maybe it's tricky, it can be done either with feature templates, or now it's done via neural models that do an encoding of all of this. And looking closely at these structures, we can see that the information that can be encoded is really very rich. Okay? So that's all I want to say about dependency parsing. I'm now going to close the lecture with a little summary. So essentially, I focused on linear structure prediction. And one of the main things that I want to highlight is that we can see structure prediction as an extension or a generalization of multi-class classification. Okay, so in multi-class, we're gonna predict the label out of the set of labels that maximizes a linear score given by the model. Okay, so in all cases, we're using a representation of the input together with the candidate label. We represent that and we produce a score. So in sequence prediction, we actually follow the same form, okay, of this linear model, choose the output that has better score, only that to make this argmax tractable, it's useful to assume that this representation is factored, for example, factored at the background. Okay, so in case we use this factorization, we can solve this efficiently, and there exists many factorizations that are tractable. Okay, so it's one way to go. This can also be thought for other types of problems, like we just saw quickly. Dependency parsing, we can employ an arc-factored approach, where again, the form of the model is the same. Okay, it's just a linear model, but we're scoring each dependency in the tree independently of the others. Okay, so again, for this factorization, there exists algorithms that can recover the argmax solution quickly. Okay, so factored models in general are applicable to other tasks and factorization. So what we want to find this combination where the factors are expressive, but then also they enable fast algorithms to recover the argmax solution, or other computations are also relevant, like the computation of marginals in the context of probabilistic models. Okay, an alternative to this is to just not attempt to recover the optimal solution, but be fine with an approximation. So in that case, we can use transition systems, which are very fast and also very expressive. Okay, but there we cannot guarantee that our parsing routine, that our prediction routine will always pick the maximum scored solution according to the model. Okay, so we're prone to such errors, but still, sometimes they have very rich expressivity by which then we can produce very good models and mitigate this with other techniques. So you might be wondering, out of all of these, what can we use if we want to use nonlinear models? Okay, so there's two places where we might want to go from linear to nonlinear. So one is in the context of factor models and the score function. Okay, so the score in a factor model, the score of a solution is a sum of scores over the parts. Okay, and so in a linear model, we're saying that this score is given by this linear function. Okay, we're providing the feature representation, and we have the linear parameters of our model. Okay, so one way to go is to replace this scoring function with a nonlinear factor, with a nonlinear function. Okay, so somehow the nonlinear model still uses some weights, but the representation is now given by, say, a feed-forward neural network. Okay, that out of some initial representation of our word in context, it kind of builds layers of embeddings. Okay, so this W will operate on an embedding that represents the context of this sentence together with this bigram. Okay, so one way is to keep the model factored. It's still a factored model, but the representation is also learned by the model out of some initial representation. Okay, so because it's factored, we can still use the Viterbi algorithm. Okay, but parameter estimation will be non-convex, so we need to use routines like backpropagation. Okay, to learn both the parameters and the parameters of the representation. Okay, the second alternative to moving from linear to nonlinear is to use some sort of recurrent sequence prediction where we have the input sequence over here, the output sequence over here, and what we want is to have an intermediate representation, sequential and vectorial. Okay, so you might think of this as a sequence of vector embeddings that encodes the substance between inputs and outputs. Okay, so maybe this representation here would encode everything necessary of the context to predict that the label on top is this one, or also maybe we could use it to predict that the word below should be this one. Okay, so this is kind of the holy grail of NLP. Okay, what are structured intermediate representations that enable to transfer information from one part of structure to another, okay, in ways that we can estimate these models from data, but also make predictions, maybe different types. Okay, but this problem is computationally very expensive, and also statistically it's very difficult. Okay, so making predictions is not tractable, so we need to resort to greedy methods or beam search. And learning is highly non-convex. Okay, so we need to resort to all the advances on deep learning in order to tackle this problem. And there's clearly been a lot of progress on this line of work in the context of NLP using RNNs, LSTMs, also spectral models. So Chris Dyer in the next lecture will show you these kind of approaches based on encoding, decoding, attention, and so on. Okay, but at the very end, if our problem is over structure prediction, there will irrespective of how we learn an underlying representation of our data, there will always be a loss function. Okay, that needs to take the essence of structure prediction. Okay, and as a matter of fact, if we look at recent works on name entity recognition, okay, one is authored by Chris Dyer. So they build this. I'm not going to explain in any detail this network, but this is some sort of this intermediate representation that we want to learn between the words and the outputs. And we see that in many of these network configurations that the layer on top is a CRF layer. Okay, so what I explained today still is a component of the state-of-the-art neural model. So this is one popular method. Here's another one of different authors that they use a different style of representations, but at the top, they always use some sort of CRF layer. Okay, and you can check the results and see that if they use a CRF or if they don't, they always get an edge on performance, meaning that the loss functions, the representations and loss functions given by CRFs that attempt to capture direct correlations between any two output labels always give an edge of performance. Okay, so essentially this is all I wanted to say, and I thank you really very much.
Okay, that was it.
Another question on the Q&A.
Oh, there is a question now. I was saying there wasn't any question. Why was CRFs not as successful in transformers? Yeah, I don't know. These results are empirical. So transformer, basically what it does is a super expressive representation of the input. Okay, that can represent a certain token and a sequence, making use of these attention mechanisms that looks that pairs that current token with any other token of the previous or even of the sequence. Okay, so it creates very, very, very expressive representations. The fact that it's expressive also has a consequence on the cost. Okay, there's this quadratic dependence between any two tokens of the input sentence. So of course, if a CRF, what it tries is to model dependencies between parts of the output. Okay, but so say I want to predict a name entity label in the middle of a sentence, and I want to make use of the previous name entity label. Well, somehow that name entity label of the previous word is also predicted out of the input. Okay, so one can think that if we have a model like a transformer that is really massively expressive, maybe that same information of the previous label somehow might get captured by the transformer itself. So that's just one hypothesis that should be tested under controlled experiments if that happens or not. So that's one case. So if one increases the representation of the input, it might be unnecessary. So if we have very powerful contextual representations, they might encode the potential nearby labels of the output. Okay, so there's this trade-off. Okay, should I spend a lot of effort in modeling the input and contextual representation of the input, or am I better off at modeling parts of the output? So clearly, since BERT and all these giant models were introduced, there's a lot of focus on the input. Okay, and actually we get it for free because we have these giant models, BERT, that give you very good representations of input tokens in context, and so maybe those already can capture, the potential surrounding labels about that. Okay, but if we go to model simplicity, that is also something that we know is important, even though now it's something that is less in fashion, let's say, even though there's workshops also now trying to come up with simple models for NLP. Okay, so I think it's all a trade-off, and eventually it depends on how strong. So now also going back to transformers, this is very expressive and powerful representation of the input that relates an input word to any other token. But in practice, that is a huge representation. So then one needs to pay more attention to the local context, put a maximum window. So at the end, what is going on is that there's some notion of let's look at everything, but let's actually look at the local scope. So what I presented today, I don't know what is worse or better. I'm saying that there's different ways you can model local scopes of the output with these techniques. Okay, and then whether that is necessary or not, it will depend on the data and the task. Okay, that's essentially that's what I think. But I think it requires controlled experiment and a good setting for analyzing both two approaches. Okay, that approach it differently.
Okay, thank you. So I don't see any additional questions here. What I'm going to do is this. So all the questions that were left in the Q&A, I'm going to be copying them and the answers to Slack. And yeah, for the attendees, I would recommend that if there are, then afterwards additional questions, they can perhaps leave them there, and we'll try to, get back to you, Javier, and in case there are additional questions, yeah.
I'm in Slack, so use Slack for additional questions that might come later. Also, I think in the labs there's some exercise that have to do with Viterbi, with many of the things I covered today. So feel free to ask there. Okay.
Okay. Thank you. So we'll be back at 2 for the lab session this afternoon. And yeah, I guess this is it. So thank you again, Javier.
Thank you very much.
Thank you, Xavier. See you next year.
Yes.
Potentially, please.
This one for real. Okay.
Okay. See you.
Okay. Bye-bye.
Bye-bye.